Hello, guys. Good evening. Stephen, can you hear me?
Hi, Nikolai. Can you hear me okay?
I can hear you fine. Perfect.
Excellent. Great.
Hi, Ramesh.
Hi.
Yeah, we're coming.
Yeah, you have to do it all at once.
Yeah. All right. Good luck with your session. I'll ask you your rights. So. Yeah, sure. Hey, work with him once in a while too. Hey, Judah, how's it going? Everyone's got one for a day, but that's my issue. Not that big of a skill.
Maybe go ahead and take a seat here for the benchmark. We're gonna start with pre-silicon benchmark.
Is Nikolai well?
Nikolai is going to moderate it remotely. He was not able to fly, so. Did we meet yet or?
We've been on a call together.
Okay.
My name is Ramesh Hashim. I work in Breakout. And so I work closely with Casper.
Oh, okay. Guys, okay. But you're flying in from California.
No, Cambridge actually.
Oh, you're from Cambridge too.
Sure.
Okay, good.
Yeah, basically taking that. Yeah. And a big focus on this is benchmarking other kids. A lot of that within my team. We have probably how do you come this firm? Once with software stack, something that can run in non-big silicon to something that megahertz, you feel like you.
We can't say like all that.
Yeah.
Let me see if I can start the meeting then.
I understand you put this.
Great. We're gonna go ahead and start our pre-silicon benchmarking meeting. I'm gonna suggest if you want to participate, just kind of sit here in the front. And I'm going to get the screen set up in the room. And maybe someone online, if you can verify that you can hear us.
If you go to school, Germany. Yes, Lucas is valid identical relation.
Lines.
You're looking at probably 20 years just. Two things. Definitely seeing what happens next.
Can you hear them?
You know, you ever heard of Peter Allen? 39 there. But leveraging design, the entertainment industry. The AJAX is called Street Scope. Objective measurement on a Caltech, Boston Avenue. We're creating a space, a simplified.
Get started here. For those of you that are in the room and it's not part of the discussion, maybe ask that you would
By the time we're done.
would take the conversation outside. We are getting a lot of background noise. And for those online, we're going to I'm going to try to angle the microphone a little bit differently. I'm not hearing anyone online. Someone could speak.
Yeah. Hey,
Yeah.
Stephen, this is Nikolai.
You.
Hi, this is Sandeep from Cambridge.
Good evening, Sandeep. Oh, I see John walking through the
Hey,
camera.
Nicola.
Hey,
You
John.
okay? How are you?
I just passed COVID. Back on track.
Is that why you're not here?
No, I was in US till last week, so I had to take
Why
care
did
of my baby this week. Yeah.
But there you are. Good to hear your voice. Hey, Nicola.
Hey, Ganesh.
Why don't we do this? I think we have. I don't have in front of me. I think it's roughly an hour and a half. It's roughly the time. Do you remember that, Nikolai? So Nikolai is, leading the start of the pre-silicon work. Maybe what we'll do, I know you can't see everyone in the room, Nikolai. There's maybe 9 of us right now. Why don't we just go around and give it some introductions and then introduce people online as well, and then I'll hand it over to you for the discussion. It's meant to be a working group meeting. It's not strictly a presentation. So Stephen Miller, I work for Bosch in product management for ADAS, but today my hat is the technical chair for AVCC.
Hi, everyone. I'm John Corintis from ARM. I lead our EMEA go-to-market team in the automotive line of business. We have a few different kind of, responsibilities in the go-to-market team, and one of them is looking at some technology strategies and kind of how we land those. And one of the ones, I'm interested in this one. One of those strategies around virtual prototyping, emulation platform, kind of pre-silicon enablement, basically. So I've been working with Nikolai and some of the Siemens guys for a couple of years now.
Michael Meyer. So I'm technical project director on one of the, let's say, projects that we're running is more in a centralized architecture. So I'm just visitor today, but I used to be on the AVCC before Elizabeth took over as one of the board members. So
Dave Myers, I'm wearing two hats. Majority of my career is as a car designer. And I got very then excited about the future of how people move around. So topics like autonomous and new business models and kind of what comes next, but making it exciting from a designer standpoint. And my current day job is a company called StreetScope, which is very technical and does depend on new software, but it has developed the ability to objectively evaluate how safe any vehicle moves on the street. And so safety and measuring it seems like it would be very important in the future, autonomous vehicle future. So I'm actually here to listen and learn from all.
Hi, I'm Ganesh. I'm one of Stevens Street. I'm a solutions architect, like a counterpart for Nikola in North America. And I come from the automotive embedded systems, ADAS, maybe active safety, function safety as well. I'm pretty new to this silicon virtualization and order representation. We are offering the solution of supporting the solution for daily software development. Reference designs.
Hi, my name is Umair Hashim. I lead a small engineering team within ARM's automotive line of business. A large part of what I do is, what my team does is we take customer use cases or automotive and ADAS IVI use cases and try and decompose them so that we can get them small enough and representative enough to run on pre-silicon platforms. We in the past used emulation and quite heavily use FPGA as well. And yeah, I'm really interested in what this working group is going to be doing, hopefully contribute as well, share some of the learnings that my team has had, some of it from our experience, and hear from the rest of the group as well.
I'm Paul Zarate. I'm with AMD. People think of AMD, they think x86, but I come from the Xilinx side of the house, where we are a ARM processor-based adaptive SoC. Again, I'm the system architect for AS and automated driving applications. And in this session, because we are trying to figure out, as we've already been talking about this morning, what do the next generation devices look like in terms of meeting the requirements for the level 3 of them.
Yeah, my name is Jong Ali from Water Intelligence Systems. We're a Boston-based company developing high-resolution digital imaging radar. We currently developed a reference system with using Xilinx AMD FPGA, and now integrating some of our processing into Versal Edge X8 platform. And our final product, we are targeting to deliver baseband basic automotive.
My name is Rohit Naria. I'm with Bosch. I'm working with Stefan also in the closed domain computing, but my area is mostly technology scouting. So I'm looking forward that what are the technologies that are coming in next to 5 to 10 years, and how we can incorporate into Bosch products or how to enhance our current product portfolio.
Hi, I'm John Cooper, and I work with that guy, Nikolai Bayman and Ganesh, and I'm a Tape 360 orchestrator here based in Detroit. New to the silicon space since a year, just learning, but I've been in ADAS since before anybody called it ADAS. So.
Right, that's everyone in the room. So Nikolai, we'll go online, introduce yourself and anyone else online.
Fine. Yeah, it's a pleasure. I'm Nikolai Wiemann. I'm with Siemens PACE 360 as a solution architect. I'm based out of Germany. I joined close to 2 years ago. Previously worked at OEMs such as Volkswagen, and that's why I also brought I got already appetite for this topic of pre-silicon benchmarking back the days when I did benchmarking at Volkswagen. And now as Siemens is offering pre-silicon benchmarking as a service for several customers. And I'm looking forward within this sub-working group of the benchmarking working group, which is usually chaired by Casper from ARM. He is out this time I'm happy to have the sub-working group here, and I will talk a bit more about the motivation later. And before that, I pass it over to maybe Predrag.
Hi, this is Predrag Djurjevic. I'm autonomous system design engineer at ARM. I have about two and a half hats. Also, one is modeling, so keeping up with the contemporary models for AE and ADAS. And then second is co-adaptation of our hardware into future systems. So like a system role. The second and a half role is really contribution to ML Commons and AVCC in terms of different recommendations, documents that we published. And the kind of motivation for this group is that naturally as we size our IP and customize the features, most of the work is done through simulation and emulation before it gets to later stages of the kind of physical IP.
Thanks, Predrag. I see the first camera turning on, Ramesh.
Yes, please. First of all, can you guys see me okay? Can you guys see me okay?
Yeah,
Yes.
good.
Excellent. So, hello there. My name is Ramesh Anawajala. I'm with Blue Fusion. We are actually building a data platform for automotive industry. It's essentially a data platform of a variety of sensors with the goal to do early sensor fusion. Today, the way we work in this industry is that the vision people don't talk to radar people. They are like a very different world, but that's not how the sensors actually work. You should be able to see, you should be able to touch. I mean, that's a measurement. That only then you can really make sense of the world. So we kind of realized this very early. And then we really understood that the biggest challenge the industry facing actually is this lack of access to this kind of high quality data from the vision and radar. We strongly do not believe that the LiDAR is going to make this thing any better because of the cost of a LiDAR is more expensive than the cost of a car. And that's the primary reason. So we are basically kind of working on the data platform. Now, when we do early fusion, we have all sorts of interesting things that we have, like how do we actually process them? How do we define the benchmarks? Because the benchmarks are defined today for AI ML of this, the computer vision algorithms. But there are no such benchmarks for radar because radar comes with its own point cloud data. So this is a kind of a primary reason that we are very much interested in this particular work group. Thank you.
And Ramesh, I didn't quite catch the name of your company.
The company name is Blue Fusion, like a one word. The Blue Fusion, it's essentially we're kind of fusing whatever that we could fuse.
Cool. Sandeep?
Yep. Hi, everyone. Sandeep from ARM Cambridge. I work on the machine learning group in ARM. I work in the pre-silicon space where we work on the system level machine learning models profiling on the ARM CPU and GPU. And that also includes analyzing the latest models, LLMs on the ARM platform and how they operate and how they are performance competent against the different competitions as well. So that's precisely my and my team role in ARM.
Rohit?
Hi. Good morning, good afternoon, everyone. Rohit. Hope you are able to see me now. Yes. Hi. So I'm here to understand more from the benchmarking point of view, what's happening in the industry. I've come with almost 23 years of experience by profession, aerospace engineer, but last 8 years I'm into autonomous driving space and represent Tata Group, supporting different vehicle lines. And we are right now evaluating different chip vendors and trying to also understand that what should be the requirement in terms of the DMIPS, the TOPS required to run the enhanced cockpit experience more from the immersive displays technology and all, AR, VR technologies. How do we give better customer experience along with the autonomous driving? So how this AD area, which is going fast, say today, industry is talking about L2 plus, L3, L4, and also keeping in the context of SDV, it makes more sense to protect the vehicle for the future needs. So you don't have to change the vehicle platform or the hardware or the chip as well, maybe with the help of chiplets that can be upgraded. But why not to think about 25 years down the stream, how the overall vehicle will be scalable and able to future proof the vehicle from the performance or the KPIs point of view. So what will be the best number? I think that's industry is still trying to understand, unless we run certain models on the chip and trying to figure it out what is the best tops or DMIPS we need to have so that can have a better understanding with the suppliers and ask for that. So that's a quick summary from my side.
Thanks, Rohit. And what's your organization again?
I'm part of a TCS, a Tata Consulting Service, and I support Tata Group, both the motor lines.
Thank you. I think the only one left is Alejandro.
Hi, everyone. Good afternoon. My name is Alejandro Ruiz. I am the Associate Director for EE Systems Architecture at Fisker Inc. Fisker, we're a startup and EV maker. And in the role of my organization, we're in charge of defining not only the up and coming electrical architectures, SDV, but also into the hardware selection. As some of the key blocks on SDV topology rely on advanced and high computing power with high throughput. So in addition of selecting what is the best approach from a systems perspective, we're also selecting what makes sense from a silicon perspective at the hardware level.
Right. Thank you. Even if okay for you, I would briefly recap what we have as the aspiration for the pre-silicon working group and the motivation. And then I would use probably the majority of our remaining time for diving deeper into getting more details in our technical report structure.
Sounds good.
Perfect.
So we're all going to be looking at the screen, so you'll see the back of most of our edits, just so you know how the room is oriented. But please continue.
All right, good. Yeah, I briefly said in the introduction, usually this benchmarking working group is headed by Casper Mecklenburg from ARM, based in Silicon Valley. I think he is on parental leave right now. We had a baby pretty much at the same time. The benchmarking working group itself already has published 2 technical reports within AVCC. The last technical report that we published was about different computing scenarios that you could have. So not only to, when doing benchmarks, consider a single neural network execution as an example, but also include other ways of Hydra nets or parallel execution, stuff like that. And actually, we have received quite some feedback on that from the industry, that this was embraced and also is being referenced in the very much ML targeted automotive benchmark task force that Predrag mentioned at ML Commons, which are picking this up and are defining more specific data sets and CNN architectures for ML related benchmarking. Within this benchmarking working group, we have established this pre-silicon benchmarking working group. And the motivation for having something pre-silicon and specifically for automotive is mainly due to the fact that automotive has still tremendously long design cycles. So rather than relying on available silicon and benchmarking that as soon as at least a samples of that silicon are available, we see that there is different needs to actually be able to benchmark the system performance or sub-element performance. We will come to what we actually want to benchmark later, before actually physical silicon samples are available. So this is aligned with our with the industry's shift left strategy to not only shift left software development or other things, but also shift left benchmarking. So the goal is that OEMs and tier ones who are usually sourcing semiconductor components should have higher confidence what they actually source. So have higher confidence that they achieve the performance and power targets that are assigned, that they achieve that with the architectural design that they have. And this was also mentioned by OEMs who are not actively participating in this working group, but are very much interested in the results and will review the draft of the technical report. As an example, is that they have in the past sourced semiconductor components, mainly compute SoCs for their ADAS, and in the future also higher automated level driving functions. But they somehow see big gaps between the promised performance numbers from some industry standard benchmarks or some approximations in comparison to what they see in the real system. So we just want to have a kind of simulatable performance digital twin. Also, this pre-silicon benchmarking can lead to cost efficiency because you might be able to select the most suitable IP for your specific application, and this IP might be right-sized so that we don't have too much overhead or pay too much silicon that is not utilized in the end, but we have the optimal size of that. The output of this sub-working group should be a technical report, and we already have a preliminary title, which is Best Practices for Pre-Silicon Benchmarking for IVI, AD, and ADAS. So you see that we already made a selection of applications towards those which have the highest compute requirements currently for both advanced driver assistance, autonomous driving, and IVI. And it should be in a way of putting best practices together so that if in future OEMs or tier ones are planning to do pre-silicon benchmarking, or multiple OEMs reach out to the same IP company regarding IP comparison and pre-silicon benchmarking, there is a better or closer apple-to-apple comparison as there might be today if there is lots of freedom in how you actually execute the pre-silicon benchmark. So the OEMs and tier ones should benefit by being better able to compare different benchmarking results, as well as that IP companies or SoC vendors or those who actually run these benchmarks hopefully have less effort if they get very similar requests from different potential customers. This comparison should be, for example, on the level of what memory hierarchy is used, how process node is specified, communication latencies, all these aspects can play into that. Should reduce effort for IP SoC vendors, exactly. And it will include use cases, KPIs, and parameter lists. And there we will have those which need to be specified for the benchmark or should just be reported so that the company executing the benchmark still has a degree of freedom, but it just needs to report what it actually used. And also it should cover additional aspects such as security and safety on benchmarks. Casper and I did a few months ago a start for that. Originally, we were aiming to do this within ML Commons, but we see that the scope of pre-silicon benchmarking is broader than only being limited to ML workloads. So that's why we are happy to have this being run through the AVCC sub-working group within the benchmarking track. There is a reference to additional slides, which interested people might want to look into. Motivation summarized once again, long design cycles. We want to shift left. We want to have higher confidence during architectural design phase for OEMs Tier 1s. They should have better comparability, apples to apples, through alignment and standardization of how pre-silicon benchmarks are run. And we aim to reduce the effort for IP and SoC vendors. The output should be our technical report with best practices for pre-silicon benchmarking. We want to define those practices and guidelines all for pre-silicon benchmarking. And there is already a high-level table of contents that we would like to follow, which includes use cases, which defines KPIs and parameters and security and functional safety aspects. Are there any questions so far about the motivation and background of this sub-working group?
Just about the use cases, is that just an example, or is that what we're defining as the scope of the use case?
This is one example. And actually, as soon as we jump into the technical report draft, which I hope we can fill a few lines, we already have listed a few additional ones, and those are obviously performance and power, which are the most relevant ones. And I'm curious if we have any additions to that list of use cases. This boot time was just popping up, and we added this here as one example of a system benchmark. Yes. Right. So first, we were in our preparation meeting for today's call. We were discussing what is actually benchmarking. What do we actually need to cover if we want to define those pre-silicon guidelines? And we made a simplification that a benchmark always consists of 3 elements. In the middle, we see our design under test, or design under benchmarking. And this could be a different kind of fidelities and hierarchies. So we could imagine that this is only a single IP with a limited model of the environment that is embedded in. As an example would be that we want to benchmark an NPU, a neural processing unit, and we have embedded that into a NOC with a DRAM controller. So we only model the performance-defining data path. But it could also be a full SoC, so there is different levels of that, and different ways how you implement that, what we will cover later. Then this will be driven by a stimulus, which should be kind of workload specific, and there is different interests that somebody might have. Either this is a full software stack or just some specific applications, and we will also cover that. And then usually within this benchmark, you're interested in receiving some KPIs on the output side. So probably you would like to see performance numbers, power numbers, and other things which you would need to define in advance, and might also have influence on which stimulus and which DOT fidelity you choose to run these benchmarks, depending on what you want to measure and compare, and also which accuracy you are expecting of those measurements. So these were the 3 elements that we have received, extracted from that. And we also made one differentiation here already. So ML Commons is doing a great job in defining a stimulus. So there, this automotive benchmarking task force is defining a different state-of-the-art neural networks, which might even run in parallel based on our last technical report and define compute scenarios. There is already a specification of how you can load the DUT via load gen, which is ML Commons specific. There are already definitions of KPIs, which mainly target currently qualitative KPIs of the neural network. So these might be, did we achieve the classification accuracy or detection accuracy of the algorithm itself? But it also includes inference latency, and there are contributors also requesting power measurements within that. And a big plus is that this benchmark actually provides a data set which should be good suited to make comparisons if ML accelerators use, as an example, different optimization techniques such as pruning, quantization, and so on, that you can still also compare the accuracy on this given data set, even though there might be different hardware-specific optimizations. So this should be not covered within this working group. The focus really is what is pre-silicon specific. And with that, I copied the following contents of the agenda proposal into a separate Word document, which should serve as the starting point of the technical report. I would quickly jump to that. I think we will now use in the next minutes to walk through this document, the several bullet points we have already captured here, and I'm very excited to hear your feedback, additions, comments, all of that. So I think this is the time to start the working group session mode and leave the presentation mode. Ramesh, I see you're raising your hand.
Yes, please. I have a quick question, actually. I'm also trying to understand this, the kind of scope of this benchmarking slightly better here. So basically, my understanding is that we actually have an ADAS problem and we have an AV problem, correct? And we do not know when this ADAS to AV is actually going to happen. But within the ADAS problem, we do have a driver in the loop. Do we have any benchmarks concerning the driver behavior or the driver monitoring or something related to basically the driver become part of the safety aspects of that driving?
Yeah, I'd like to pass that question to Stephen because I think it's less pre-silicon but more benchmarking and generally related, right?
Yeah, exactly. And no, I mean, it's a great question. So this session goes till 3, then we break 3 to 3:30. Then at 3:30, we'll come back for system benchmarking, and that's exactly the kind of input we want there. What are all the pieces for a full system benchmark, independent of whether it's done pre-silicon or actually in a physical, hardware system. So I'll make that note, but hopefully you can join us for that session as well, and then we'll include that.
Great. Very good. So the first chapter of this technical report is to serve as a list of potential use cases where you would like to run pre-silicon benchmarks. And actually, we have boot time now listed here only as a sub use case. So the ideas we covered within this smaller audience preparation meeting was that we see the most prominent use case being IP performance and power benchmarking and system performance benchmarking on the first two bullets. On IP performance and power benchmarking, we see the industry, several customers, as an example, comparing different NPU architectures next to each other. We see this also slowly moving into the area of other IP components, other than those only being used for NPU, for neural network execution. But that's currently the most prominent one of doing a benchmarking and comparison of IP. Is vendor A better than B or something like that on an IP level or system level? In this case, actually, probably it's good to specify this could be a system on chip, could be a system in package, so a chiplet-based system, stuff like that, to compare performance here. And we see that there usually is performance targets being assigned, and that could be boot time, but that could be power targets, that could be latency requirements, that could be throughput requirements, and we have a detailed list of those KPIs later, but just to have a rough list in the beginning here.
So,
and then
I just had a quick question. Your initial use case was like startup for like a review camera, for instance, which is kind of more on a system benchmark standpoint. And this is the pre-silicon benchmarking. Where do you split the two between a pre-silicon and a system benchmark? What is your kind of, how do you set the boundaries for one versus the other?
So both should be run pre-silicon. I think the differentiation we made here is how much is modeled accurately. So in the IP benchmarking, at least we at Siemens, and I'm looking forward to for any other contributions here, is that if you only want to do an IP comparison, you just take the NPU, and in the best case, there is RTL available for that, which would be a very accurate representation of the design, which should be cycle accurate. And the other elements we only model are the interconnect and the memory. So we only model a subsystem, which is defining the performance target that this IP can achieve. Whereas the full system performance, and the example listed there was boot time, should include many more elements. So we would need to have the CPU included, different peripherals included, which might be initialized, and so the number of elements, the size of the design under test simply would be much bigger, and might go from only a sub portion of that to the full system.
I think my view on that is it's a use case, right? The use case can appear in both pre-silicon and system level benchmarking, right? You could do a system level benchmarking in pre-silicon as well. That's
yes.
So it comes down to, again, it's a use case. Again, the point I think that we want to then differentiate between is IP level performance. Is pre-silicon benchmarking restricted to IP level only? Or do we want to include system level benchmarking in pre-silicon? So those are two different things, and I think maybe we want to provide some clarification. I think it would make sense to have system level benchmarking in pre-silicon as well, if it was possible. I mean, isn't that would be the golden goose, right? I think that's what we are all chasing.
Yeah.
But maybe let's not strict pre-silicon benchmarking to IP only. Again, if we, and then I guess the other thing I want to try and understand is, are we currently just looking at creating this document, which is a guideline and best practices, or are we also, is there a plan to, like how we did for the benchmarking work group, have a reference use case and a reference implementation of that was basically produced, right, with the ML Commons infrastructure, which you can just go off and then run as a container. Is that also within scope, or are we first just trying to get this document out about the guidelines and best practices?
I think based on what AVCC did in the past, the document is definitely the starting point. It should serve as best practices and guidelines, as you said, like a non-binding guideline. We're not currently aiming to provide any other things or sources or systems to integrate or something as part of AVCC. But it's a good point. So if there is something like that arising, it would be actually very nice to discuss if we have something specific in mind which might be valuable to help with these pre-silicon topics. Like ML Commons is providing the data set and reference implementations of those models. If there is something similar coming up here, which might be applicable to many of these pre-silicon benchmarks, that is very valuable to discuss, yeah.
Is it worth splitting IP and system as two subtopics within this to say pre-silicon benchmarking? This is if you are for IP related, if you want to focus on just the IP, maybe you have one section, and then for system level you have separate section, because I think the paradigm and the way you go off and there'll be some bits which will be common, obviously, but as you delve into the details, you may have a fork in the methodology and the guidelines that are set for IP only versus system benchmarking in pre-silicon.
Yeah, I'm just.
I think the AVCC has both the what you would call the IP and kind of recommendation for the system or parts of the system, right? So one is the data sets and models recommendation. The other one is scenarios recommendation, which doesn't still describe like the entire system because that's kind of the sunny day goal, but it does provide some recommendations on subsystems that do some tasks within the vehicle, complex tasks. So there's probably 3 levels of complexity here, going from IP to these kind of miniature or mini subtasks that can still complete a task, if you will, and then like the entire system, which is again questionable how much of it and to what fidelity can you basically simulate to emulate in the pre-silicon.
And I think
just to add in, may I go, Nikolai?
Yeah, go ahead. Yeah.
Yeah, so in ARM, we do the system level performance analysis and the power analysis in the pre-silicon, as you were all discussing. The main challenge what I see is that in the system level, it is not actually in the pre-silicon, the system is defined. So you don't know the later on how the changes will be and how the interconnect and how the different peripherals will be behaving. So we can get at a IP level performance, and then we, be it CPU, GPU, or any other IP component, and then we try to extrapolate on a different connections and try to get the system level benchmarks. So in ARM, at least in the machine learning models, so if we define a stimuli, then we can compose accurate figures for the different IPs, and then at a system level for the ARM IPs, how the model will behave. So that's how, at least in ARM, we try to do both, mix and get the figures for both.
When you say model, do you mean neural network model, or do you mean the IP model?
Yeah, like machine learning models. So how we do it on both actual model, like fast model kind of model, which are bit accurate if they are. Otherwise, we do it on the FPGA predominantly. So yeah.
And the AFM models are used for performance benchmarking or for functional benchmarking to model
performance
quantization?
It's mainly for the performance modeling and also the power.
Okay.
Sorry, Sandeep, I think Nikolai's question was, are FVPs that you mentioned, are they used for performance analysis? I think that's not the recommended use case for performance.
So what for the bit accurate performance, that's what I was trying to say. So when we want to like a bit accurately, means performance accurate systems, we use FPGA mainly for the numbers.
Yeah. Makes sense.
I guess you can, I think you touched upon this, Nikolai, right? There's 2 aspects of performance of a model. One is the accuracy part, which is not constrained to the timing of it. That performance, how well does it perform to detect or to predict? And then there's the performance of how fast it runs. I think that's what Sandeep maybe was trying to address.
Exactly. So the one is like quality performance on algorithmic level, and the other is latency, power, PPA, typical measurements we do on hardware side. Yeah. Okay. Yeah. This is just a recap of the definition, stimulus, design under test, the KPIs. Is there anything to discuss? This should serve just as an overview of how this structure looks like, and then the 3 subsequent chapters should focus on each of these blogs independently and go into details. So on the
still the overview kind of mixes the system and other benchmarking, at least the way it's written in several cases. So is the goal out of this to really come up with where are the boundaries and add that a little more clearly within the documentation that's going to be provided?
Well, I don't know if we're necessarily looking to split system versus system element, right? I see it as one will build on the other, right? Probably start with the IP portion, so like the NPU or whatever it is. How do you specify that? But then I think ideally we would then cover more of the full system, but it would be the compute system, not the vehicle system, I think, to be clear.
Yeah, no, I understand. I'm just.
Or I mean, there's something what is it that you're thinking about here? Like,
I'm just thinking you're doing one and you're building on it. You do the system benchmarking, it's the second part. The way it's structured in this kind of meeting is we do the pre-silicon and then focus on the system benchmark as the second portion. And it's the expectation that we do this kind of pre-silicon benchmark and really narrow the focus. So we just having a dialogue around this and say, all right, maybe it's an opportunity to expand this kind of pre-silicon to a system level benchmark. I'm struggling with it.
So when we talk, so in this later section, when we talk about system level benchmark, that's completely independent of pre-silicon. That's more maybe fully defining what we would want in a system level benchmark, but that could again be on existing hardware. But within the pre-silicon piece, I think asking, well, what are the pre-silicon things you have to do a system level benchmark? So let's keep, those are, I mean, they're, obviously related, but they're not meant to be the same document, just to be clear.
Well, let's try and think about it from a slightly different perspective, right? There's two ways we can think about this. One is if we take a top-down approach, right? You say, here's my application, which runs in this, say, Linux-based environment, right? Now what we want to be able to do is predict how fast this application will run on this future design that I'm going to be taping out at some point. And I guess that's one of the goals, right? I want to see how fast my application will run on my future silicon. And for that, you have to basically start, decomposing it down. And then eventually you would draw the lines, okay, this will eventually boil down to some kind of IP level benchmark or stimulus, which you're measuring KPIs on. Right, that's one approach. The other way is, okay, let's start at the bottom. Here's my IP. I am predicting this IP to give me X% uplift in whatever function that IP performs. And then you build a framework around that. And then once you've done that in pre-silicon, but when you're doing that in pre-silicon, you're potentially just providing hardware stimulus and looking at how well it performs on the other side. You'll get the KPIs. And then do you take that approach where you start building up on top of that? Or do you take the bottom-down approach where you say, here's my full stack, let me try and decompose it. It'll run in the same environment, or I try and reproduce that environment in my pre-silicon space and see how fast it runs. We at ARM do both, depending on which team you're in. Our IP teams will start with the bottom up. They design the IP, they'll build the framework around it, and they'll give it stimulus. They have all the instrumentation into the IP, which will tell us how fast it's performing. And we'll have some data points from the previous generation to tell us what the uplift is. Now, that's again at a very IP level. As you go up the stack, obviously there's other components like the software, the other bottlenecks in the system, which will play a part in the overall performance of that IP in the whole system context. And that's, I think, what we try and do within my team as well. So in my team, we take a bottom-down approach. We try and take some reference application, do some, we analyze it on real silicon and try and decompose it, break it into smaller, identify where the bottlenecks are, try and reproduce those bottlenecks, which will try and exercise the part of the system that is slowing it down potentially, and then we'll find ways of either improving it, whether using newer versions of the libraries that the IP it's targeting uses, or better system level code, or just rewriting some of the software to make use of the newer features that the new IP brings. So I don't know if that adds. That's just one way, one method, like one way of doing it. That's just from my experience. I don't know whether we want to.
And I can fully confirm what you said. I also see both being deployed on our side by customers or through us as services. And I think I hope that this technical report is covering both. Wherever possible, cover both and only highlight those when there is differences between these two approaches. So probably, as you said, like there will be differences on the stimulus side, obviously on the complexity of software that is run, on the amount of modeling on the hardware side. But eventually the KPIs we do is, for example, the same. And in that way, we try to cover actually both in this report, and only have those branches, let's say, where applicable. Okay, so and I think there is already a perfect leap into the first.
Nothing here. He's like, can tell he's thinking.
We're almost defining the constraints with the IP benchmark, right? And then the system benchmark, we're kind of optimizing to the constraints for the most part, right?
Sorry, can you say that again?
We're kind of defining the constraints with the IP benchmark, and then we're optimizing to those constraints with your system benchmark for the most part.
Yeah.
So I think the IP benchmark is pretty much just setting the ground floor. These are the constraints in the system. And our system benchmark is pretty much, we're trying to optimize everything at the system level to work to those constraints that we've already defined at the base.
Right, and I mean, the other way I would think about it, right, is if I'm the OEM and I'm like, okay, is this chip going to meet what I need to do for my system? So typically now would be, hey, get me the eval board and I'll run something on it and just measure that, okay? But obviously, in terms of this kind of thing, we would like to say, oh, for these systems, this is what, okay, well, then my next system is going to need to do more. So this is what it needs to be able to do. And the earlier you can say that, the design cycle, then that helps the IP designers and the SoC makers, and they answer the question, will this meet the requirement for the market or the industry before I've actually built the thing? And so I think those are slightly different ways to do it. I think for best practices, there's also the nitty gritty of, is my RTL or my MPU actually, what's the performance numbers there? So I kind of see it maybe going both ways. You can get the right industry constraints. If I also think about what does it mean for best practices, right? The industry needs to properly specify what it needs to evaluate the system or the chip, so power, compute, latency, runtime. And then I think the SoC design tool side needs to kind of come up from maybe the bottom, right? And say, well, these are the tools that we have to try to answer that. And then this is going to be how we estimate power, and hopefully we can bridge that gap between the two directions.
I do struggle with the benchmark without the context of the system. And I mean, Nikolai, in your slides, you mentioned use cases. I think that's where it all starts. Because it's I can tell you, hey, we can infer 22,000 frames a second on this piece of NPU, on this particular NPU IP. And that's a great thing, but it's really, well, how many different cameras do you have? How many of them are synchronized so that we could do batching? What is the number of parameters that we need to bring in so that we understand what the bandwidth requirements are, and you identify where the bottleneck is from designing an actual SoC. So I just think we need to be careful about that first benchmark that's just shown in that simple 3-block diagram that you have, because I don't get the context out of that.
So there is both in the scenarios recommendation as well as in the ML Commons types of benchmarks. There's some of that. So it's not just one input, one output. There's all sorts of other flows, if you will, multiple inputs, whether it's basically a batch or is it multiple inputs in a sequence and so forth. So I think, again, what Nikolai has is maybe just kind of a very generic view of things. These details are really kind of more extrapolated in some of these other groups that deal with specifics of what is the input, what is the model, or multiple models, what is the output. So there's a little bit more specificity, but just in a slightly different group.
Mm-hmm.
Again, I think what I'm trying to think through is how will the guidelines or change based on the use cases? Could that have an impact? Because the way you would basically stimulate the device, the way you would capture KPIs, would that change based on what use case you're doing? That's what I'm trying to try and reconcile with. Because coming back to the split between IP versus system use cases and the methodology and the guidelines for those two may be different.
I think that
it's a question. I'm not sure if I have the answer to that.
My own personal.
Well, it will change if. Go ahead.
Go ahead, Frederick. Yeah.
Meaning on a top level, it should cover both the IP and the system level. So if you're talking about things like latency or throughput or power, so forth, those things are going to be there in one and the other case. How specifically you're measuring will change based on the specific scenario that you're doing here, right? So if you have single input, single output, the latency and the throughput are pretty clear how to measure, right? If you have multiple inputs, then things change. If you have multiple models, then things change in terms of how you're exactly measuring, for example, latency. So, for example, if as you mentioned, all the sensors are synchronized, and you can put it in a batch, and that's your stimulus, and then feed it in the model, then you can get the latency in a specific way, right? If that stimulus comes from the more sequential kind of input, then it's more of a different type of measurement for the latency. Similarly, if you have more than one model for the same stimulus, so let's say you have one image that is dealt with two or more models, right? How you're going to measure latency. Each of the models may have slightly different latency based on the complexity and the size, right? So how you're measuring latency. And then finally, if you're doing any kind of pipelining through the system, that also complicates things because latency versus throughput is not as correlated as it was one-to-one. So on a more detailed level, I think things change. On a very high level as to what KPIs you are going to collect, I think they don't change because, again, if you just split them into some of these time measurements and power measurements, I think they're common between these. But in more detailed view of things, I think things will change how you're exactly measuring things. So setting up things and how you're measuring things.
And I was imagining that eventually to overcome this challenge that you were highlighting, like that these guidelines include basically a chapter, for example, in the beginning, that if you want to run a pre-silicon benchmark, you do need to do an analysis of these elements which are influencing the KPIs you are measuring. So let's say if we want to benchmark an NPU, then the analysis would probably show that if it's a loosely coupled accelerator, that the main other specifications required would be the bandwidth of your NOC or your memory access that you have. And then you can basically decide based on this investigation, okay, I need to model somehow the interconnect and I need to model the memory controller. But if you see that you have a tightly coupled accelerator, which is also heavily relying on interrupts to some other processor, then obviously you might need to model that also in a specific way. And these guidelines should help in if you do IP benchmarking, you always need to have a system in mind, as you said, right? And to come up with that, what actually needs to be modeled of the system and how accurately each of these parts of the system need to be modeled, that should be like guided by this, yeah, if you can have a virtual CPU or you actually need to have an accurate CPU to do some measurements, and maybe that way you somehow have a subsystem model if you do IP benchmarking. On the full system benchmarking side, actually, I heard sometimes you might want to optimize the systems and so on, and that's interesting because it's leading towards using benchmarks pre-silicon for system workload co-optimization, I would call it, some high-level hardware software co-design, which might be an appropriate use case. And I would like to add to the list of use cases above, because the original idea was that eventually it's really just that there is fixed IP or system configurations, and you just have to select or compare between those without actually having a feedback loop from your KPIs into the system or IP optimization.
I think that makes a lot, at least to me, makes a lot more sense. Have the system level benchmarking kind of distilled down into pre-silicon, and that shows good synergy as well, right? So I think that's what you were also trying to say, Nikolai, right? Where we, maybe that's a good, and it shows continuum between system level benchmarking, hopefully, which we will discuss later, right? And we can have that continuum of methodology saying that, okay, this is how you do system level benchmarking. Once you get to this point, you can start to have that crossover down to pre-silicon domain. And how do you continue the analysis down in the pre-silicon environment? And then also, again, and I think that's the main problem that the industry is trying to solve, right? To predict how will my system perform, my compute system perform, which is running my application or my implementation of my application in the next generation of silicon. So that kind of really addresses a key ask from the industry. And maybe the suggestion for having the IPs focused benchmarking can, again, be a further level down from pre-silicon benchmarking of system to can be a follow-on from, once you've got all of that running, how do you then further go down the IP level?
Yeah.
Have like a waterfall kind of documentation saying that, okay, this is the full big problem, you distill it down to run in pre-silicon, and then you further distill it down to run pre-silicon IP only. Maybe that might be a good flow and shows a good roadmap.
Let me add to the waterfall. Our boss, like David Fritz, he presented this software-defined vehicle digital thread workflow, right? We're planning to use a DevOps workflow, right? Instead of the waterfall. We don't have to define everything first. It will be incremental, right? So the system, the hardware, software, it incrementally gets defined and it feeds to this pre-silicon benchmark, and the iteration happens. That's how it is going to fit to this agile methodology and DevOps workflow, right? So we cannot define everything. We don't know everything.
Yeah, and you can have like a CI/CD framework at each level
right? And the system are at different maturity levels now, right? Say, for example, we're talking about ADAS and IVI for silicon benchmarking for the SPV architecture, but the mechatronics side are going to be somewhat unchanged for now, right? So you'll have different maturity levels, different fidelity levels. So this digital threads from the requirements of the PLM, ALM side need to flow back into this pre-silicon benchmarking for future hardware, right? And it again iterates by itself to get to the next maturity level. Yeah, so somehow we have to combine pre-silicon benchmark and system benchmark. I think the industry is moving towards this DevOps methodology.
So maybe, I mean, because you work in this, I mean, this is like your day job, right? So like, maybe describe a little bit then what the challenges are that you have, because, you know, obviously, you know, there's lots of IP around and a lot of, you know, that's made it into silicon. Like you have measurements against IP. So there's a certain amount of knowledge, you know, that you have that's useful. And then when you think about designing a new system, or if you think about why a system didn't achieve, you know, or wasn't enough, right? Yeah. Maybe just talk a little bit about what that is and those pain points in terms of what we would want.
I haven't come across the situation where you end up designing a system that hasn't performed. It hasn't been a problem that we have had to deal with yet, because ARM has traditionally provided the IP, and that goes off to our ecosystem. But they feel that more than, say, I feel it in my, how happy felt it in my day-to-day job. That said, I think
you've done work on helping partners to optimize.
Yes, that's
those workloads where they haven't been
right.
The performance that you expect.
So what we have basically done is what we basically, they've taken the design choice, made their design choices, right, and built the system. Now then they come back to us, and what we have helped them do is, okay, you made your bed. Now this is how you can extract the most performance out of it. Let's make sure that whatever route you have gone down, you can extract the maximum amount of performance out of it. But that is changing now. We're looking at to be more proactive in that space, you know, and address that problem upfront. Now, as I said, right, our methodology has so far been about taking the application, getting it running on the closest silicon platform that we can, and then we start using performance analysis tools like Perf or ARM Performance Studio. VTune is the Intel's equivalent of it, or x86 equivalent of it, but we don't use that. But it's something similar, right? So that helps you provide a landscape of the overall workload and where the workload is spending most of its time. So identifying bottlenecks. So get it up and running on closest silicon. Use performance analysis tooling to identify the hotspots, which can sometimes be on the accelerator, it can be on the CPU side, it could be on the memory. It depends on just the implementation of the application of a particular customer's or vendor's application. And then you go off and say, okay, how can I reproduce this bottleneck? How can I decompose this and isolate this bottlenecking data path or code path and reproduce that as almost, think of it as a test case, which we then optimize on, say, let's use an example for this, right? We have this new instruction called, a new architectural instruction extension called SVE2, which is a vector extension. Now, a lot of our previous generation cores did not make use of that, so the application were written to utilize it. What we did was we looked at how would that help alleviate some workloads. Now, it's not a silver bullet. In some cases, when we implemented that data path or code path with SVE2, we saw a drop in performance, but in some use cases, we saw an increment or uplift in performance. So it varies. So what we do, sometimes it's a memory bottlenecking issue. So maybe you need bigger caches. or you need a higher bandwidth interface at one of the cache levels. So it's different based on where the bottleneck is or where the application of the code is falling in hardware. And then we run it on. So we don't often have silicon for the platform or this feature implemented in silicon. So we then resort to FPGA platforms, which are our own in-house FPGA infrastructure, or we rely if the IP is mature enough for us to have an FPGA implementation. Sometimes it's not mature enough, so we run it on emulation, which is the step that comes before it's being implemented on FPGA. Again, the further up down you go, the slower it gets. So there's more and more incentive for you to decompose that application down to something which is reproducible in a platform that is running at hundreds of kilohertz or a megahertz instead of gigahertz. So that's the challenge. How do we identifying the bottlenecks, optimizing those bottlenecks, and showcasing it on pre-silicon platforms which may not be available.
And this is very interesting, and maybe I can ask a few follow-on questions to fill out these three areas here. So you were saying your stimulus is an application. Are we talking like some specific benchmarks targeting SVE2, or would you be running full software stacks such as AutoWare and observe like what percentage you can optimize on? What is your stimulus?
Unfortunately, we don't have benchmarks, right? We wouldn't have AVCC if we had benchmarks, I guess. But no, what we try and do is, again, it's the automotive software ecosystem is quite fragmented in that sense because everyone's doing their own thing, right? Now, the infra or the infrastructure use cases are pretty well defined, and we have SpecInt, for example, which is quite representative, or SpecFP, which is quite representative of the kind of workloads they run. If they're able to show generational improvement on those benchmarks, it often translates to real life improvement. Same thing with on the mobile side, you've got Geekbench and Antutu. These are pretty well defined. The use cases are well defined, and how they are deployed on the hardware is also pretty well defined. Now, in the automotive side of things, right, it's like the Wild West. How you want to partition up your stack is entirely up to you. How you decide whether you want to run this much on the GPU, this much on the NPU, and whatever on the CPU. How you partition your problem is, and how you optimize them is often implementation defined. So we don't have that kind of standard benchmarks. So we have to take it on an application specific or implementation specific. So it can be an ADAS application which is performing the same function, but the implementation may be completely different, right?
Depending on customers.
Depending on the customer's implementation. How much of the sensor fusion do they do in the stage before or after?
And how much the OEM wants and how much the tier one wants.
Yeah, and how much performance is available? Do you have a larger CPU cluster? Do you have a lot of performance or single-threaded performance available on the CPU side? Then you can try and run more on the CPU and less, have a smaller NPU, for example, and you run a smaller part of it. But if you have a larger NPU, you can say, oh, I'll actually put more of this front end of my AD pipeline on the NPU.
It's lazy.
Yeah, so it's so specific.
Because the software is adapted to the hardware.
Exactly.
Well,
or sometimes it's not even. It's
more. Sometimes it's.
So yeah, sometimes it's legacy.
Most of it.
Sometimes it's legacy. Yeah, I mean, I remember seeing a demo where someone had their chip and they were showing more of a full end-to-end AI application planning and trajectory. It was all done in AI as well. And they're like, yeah, look at this is great. We use the MPUs and like almost no CPU cores, and they had a lot of cores on the chip. Yeah. And my thought was that's a waste of a lot of cores because but that's probably where things are going in terms of AI for everything.
And you may over provision on the CPU side, saying that actually, you know what, I'll maybe add more features to my application, which will run on the CPU.
Right, which would be CPU, right? So maybe they weren't showing everything they were going to do, but it was just interesting how this was a big point they made. Like in the past, a driving software stack would have used a lot more CPU for all the planning. And now that's
well, I mean, you also have to have margin of utilization, right? You cannot sacrifice, the variance of the latency because you want to have high utilization, right? Now, maybe you've seen very low utilization. It doesn't explain that, but certainly for the automotive and aerospace and any very highly sensitive and safety environment, you can't max out the utilization. Otherwise, your variance is going to be dangerously approaching the deadlines, and therefore there's a little bit, you have to dial it down a little bit. The other things are really what level are you at, right? And that will determine what the models are, and then therefore what the sizings of your NPUs and GPUs and so forth are, right? So that will determine the sizing. So application itself also has to be in context as to what level are you trying to address. Are you addressing safety and other things, right? So and then, as you mentioned, the style of the system itself, right? Is it mostly early fusion? The late fusion? Different companies have very different philosophies as to what they think safe way of doing things, a perform way of doing things. So you're in this multi-dimensional space of things as to how much loading, how do you want to do it, which models you want to take, and so forth. And really, what you have available is an IP, right?
And then there's also the question of the operators, right? Your model may evolve, and the kind of operators it may end up using may change, or the distribution or the graph may change, and that will impact utilization, or potentially, you may end up improving utilization of your NP, or you may actually go down the other way. So, but you want to be able to.
I mean, it's a feedback loop, like software.
Sorry, Pedro, your connection is quite poor. I think we lost you, and you were breaking up as well.
Yeah, also on my end, Frederick, I think we lost you.
I think your comment about things changing and everything else then leads back to the point that you were making, Stephen, which is are you optimizing for a system which you haven't had, or are you trying to understand what future system you need based off of the work requirements? So it's a kind of evolution, right, of the that's really which comes back to what the actual goals of this. And are you trying to do both of those things, or are you leaning towards trying to understand what future silicon platform you might need based off of? That's actually your expressing technology.
Yeah, like a good example for that would be transformer-based models, right? I think previously it wasn't so transformer heavy, but now that's changing, right? And if you had an NPU which was not very good at transformers, you'll end up seeing a performance bottleneck. But if you had an NPU which was good with transformers, at a high throughput with transformers, improvement in performance, because that's where some of the models are heading. Yeah. And the space is constantly changing as well.
That goes to the offloading comment.
And I'm excited, like you said you also have your FPGA models. Like, which are the elements that you model with respect to performance? You have your CPU IP, and then an ARM interconnect, and then some memory latency model, or what do you model for performance? And which?
Excellent question. We have multiple, because the FPGA resources are expensive. So we end up having different levels of modeling. So we may have a very simple, the one that you spoke about, right? Just the bare bones of the model of system to be implemented for you to test the device under test. We have those, but we also have full system implementations in the FPGA, which will take up multiple FPGA racks, tens of FPGAs. just to implement the entire system, which we will then load up as much as we can. Because there's a lots of other metrics that we need to measure on, especially our interconnect IP, right? We have to measure freedom from interference, quality of service. How do you do that without actually implementing an interconnect and loading the system up to see how it performs under stress? So for that, we need our full. We obviously can't run full application stacks. We'll maybe, to give you an example from the GPU domain, right? We'll render a frame or two to see how it reacts, or really one heavy rendering scene or a few heavy rendering frames, which will take hours or sometimes days or weeks to run, to see how it performs in that peak load time frame. And we'll load the CPU and the memory system with all the other things to see how it deals with the stresses put upon the system.
That would be an FPGA implementation or just a simulation?
So we do both. We have performance models of our interconnect, which we will stress out and then stress up to see how it performs, and then we need to correlate that performance model with the real RTL implementation to see whether when you measure cycles on the RTL, does it correlate or not? Is that the pilot?
If I can just take a very quick tangent.
Yeah, absolutely.
Have you trained an AI model to do your model? So, right, I think of some of these weather predictions that have actually gotten quite good and quite fast. They have some ways to do, let's say, I guess not integer, I don't know, like to model highly complex physical systems, and it runs 10,000, 40,000 times faster to predict weather than your full-on traditional.
I'm not aware of how much it's used in the other parts of the business. I know we use AI models to fill in some of the gaps. For example, we have test configurations, but we can't test all the configuration for performance. So we use AI to try and fill in the gaps in the performance model, or the configuration space, to say that we try configuration A, configuration B, and C, and there are other combinations in between. We use AI to fill
AI to interpolate. Okay.
Just more like it's a mathematical model. You can call it like that, but that's what AI is in general. So you can call it AI, you can call it statistics.
Okay, yeah, maybe.
And the EDA methods.
With
More the EDA thing.
Okay.
What Nick and I can say about what Siemens do, but I think there's more and more tool.
Yeah, I mean, that's on the tool side. I mean, kind of thinking about this broadly, I think there's the asking the right question, meaning what are the use cases that are the appropriate ones? And by use case, start at the OEM level, but maybe at the compute level, it's streaming data versus like highly interrupt-driven processing or something, right? Those seem like they're you end up modeling them quite a bit different.
Yes.
And then the other part is I would call it asking the question in the right way, meaning sort of then how you, which is maybe more the tuning piece to pull out that.
Yeah.
A lot here.
And also, I was very excited about the things you mentioned that you were measuring as KPIs. You were mentioning things such as obviously latency, but you also mentioned freedom of interference and quality of service. What are the other things all the things you're typically interested in doing pre-silicon benchmarking KPIs?
Real-time analysis. That's another thing. How or measuring real-time performance.
What is real time for you? Like you have a latency goal that you have to hit to be counted as
Application
real
and use case specific. I don't know, Pendrag, do you have it? Any thoughts on that?
Well, if the application is complex, it may provide its own interference, so to speak, right? So if you're doing all sorts of things in the application, whether you're putting it on a different IP or you have to do operator offloading or you're doing, things that cannot be executed on one IP and in a relatively straightforward fashion, then you get enough interference even to yourself, right? But the more common case is maybe the application is not as complex. It's doing one thing, one task, if you will. But you certainly know that other things are happening in the system, either because there's other models that need to be executed in parallel, or you have some kind of pipelining in the system where one phase is done in one model or one component, the other phase. And so there's always activity happening. And the freedom for interference is giving the either known or roughly modeled load on the other models, if you will, but still sharing the same IP, same hardware components. What is the variance in terms of latency, for example? That's pretty much a distribution. It's, if you look at the graphs, it's always, some kind of Poisson type of distribution, or really kind of exponential. That usually means long time of simulation, right? To catch all those, below 1% occasions where you blew through the deadline. And then you have to go back and adjust the software itself, right? If you see that you're hitting the deadline that much, then you have to adjust so there's a little bit of a loop there. But I think to make this manageable, at least in my mind, it's kind of hard to run more than one application in simulation itself. I mean, of course, yes, if you have FPGAs and you have a cluster, big cluster of FPGAs, maybe you can fit it, that's ideal. But in, I don't know, more practical sense, maybe these other applications or the models, as we usually call stressors or aggressors, are kind of not really executed per se. They're kind of just loading the interconnect and memory just to serve as a proxy to what the other applications or what the models would normally do in the system. So you kind of focus on one application as running the code, and then maybe the other application, because maybe it's not practical to run them all at once, you kind of characterize what they do to the system internally, and then you kind of simulate the loading kind of in a more record playback fashion. At least that's kind of my understanding.
On the other pain point.
And to be honest, I forgot about this. You also have to be careful about the application. At what level of optimization is it written, right? Is that the mature code that's actually executing perfectly, almost perfectly, what the IP or the model is needing, or is it kind of some open source source code that has been barely optimized, and then maybe you're not focusing on the right bottleneck, if you will. So unless you have a good code, if you will, for that application and a good compiler, have to be careful that you're not chasing something that was kind of could have been more optimal in the code itself. Sorry.
I think you're right. The representative workload is the workload that you're using to test. Is it representative enough of what you exactly intended to run on it? But the other pain point is also trying to, because again, if you want to, it's challenging to boot a rich stack on these FPGA platforms. If you have tons of microservices running, which you would have an OTA agent, for example, running, and all of those services that are running in the background, it's often really hard to load the system up with all of the rest of the software, background tasks, and so. And then again, it's a chicken, and you would ideally want to get more realistic results, but also you want to try and strip your OS or whatever system you're running to try and make sure you don't you get better simulation or emulation or better runtime, because you're not wasting cycles. running a piece of application which you don't really care about, but you're not actually analyzing.
Yeah, I think if you're playing with utilization that we talked about like 10, 15 minutes ago, and you're trying to maximize that too, then it will take a long time just to get the extreme variance that you can get, right? So it's, you get 99% of what the variance is early, but then you have to wait for a long time to get that, the more realistic outliers, if you will, that are pretty much crucial to when you're trying to certify for ASIL kind of certifications as to, are you ever reaching these deadlines? How often are you reaching them? How are you mitigating them, and so forth? So I think that actually chews up a lot of time if you want to be very scientific about it.
And does that mean that if you run these benchmarks on an FPGA, you would just prefer to not have an operating system below and try to execute it bare metal and coming to the point of interest, I say, in the benchmark as fast as possible? Or would you somehow model this and include some additional latency, or just exclude it? How do you handle that with the OS?
It would depend on the level of abstraction you're trying to do the analysis. Again, it comes back to the IP and system level question, right? If you are trying to just benchmark or analyze the IP itself, you want to just skip all of that and just get to the bit that starts running when my IP kicks in and then stops and my workload finishes. But if you want to measure system level performance and overall system in pre-silicon, then you would want to put the OS but not too much of the OS, but like a minimal kind of implementation of the OS so that you save on execution time in the FPGA domain.
And
that balance is tricky.
One follow-up on that. Are you also using hybrid platforms or time slice platforms, like booting on a virtual model, which might be substantially faster than the RTL, and then switch over to RTL, or that's something you don't do?
Not within my team, we don't, but I know other parts of ARM are exploring that for sure.
Okay.
Maybe, Nikolai, under the stimulus or workload, what I was interested in, you'd mentioned that some other areas, cell phones, was it? I forget what else, have like good representative workloads. It might be interesting to capture that in the document as well, like kind of best, whatever, essentially describing what other industries have, and then that might motivate to do automotive.
Yeah.
Right, but
you
setup
are,
is
Steve,
a little different, right? Because you're not safety critically doing stuff, right? You're usually doing one application, and there's many loose things there, right?
No, I think what Steve's trying to say is use it to highlight the problems.
Right. When we write the document, give that as an example of what other industries have, describe the gap that we have in automotive, and then the point of this is to help define what that would be.
You're referring to the hint of like a SpecInt and Geekbench and so on that were mentioned, Stephen, or?
Yeah, right. I think you're mentioning Spec. You mentioned another one. I didn't catch the name of it.
And Geekbench. Those are the two. Spec for infrastructure and Geekbench for mobile.
Okay.
I guess
I have
something.
I have a slide on this. I'm just trying to see if I can find it.
Actually, I'm also very much interested in that slide. And Stephen, what I'm just wondering if that's something for the pre-silicon group, or that's already leading towards the system benchmark working group that they were teasing to follow this one.
I think the problem is the space that my team operates in covers both system and pre-silicon. So I think whatever perspective I give will end up leading into both of those domains or have overlap. So.
Well, I mean, if it's used in pre-silicon, then yeah, just maybe as a reference, just, like other industries have solved it using these kinds of things, but we have this different. obviously, I mean, if I'm just kind of thinking, right, for the use cases, I mean, I think we've mentioned most of them, but like that boot time is an important one. So that's like one use case.
But then that's going to be very, very boot flow. It depends on what your boot flow looks like.
Yeah.
And everyone's going to have, and most silicon vendors have their own boot flow and their own root of trust and their own boot flow mechanism.
That's hard for an IP. Well, yeah, but I mean.
That again becomes a system level thing.
Yeah, but then maybe that's not something that you worry about, but I think it's still something an SoC designer has to worry about. The SoC system does need to answer that for
absolutely
automotive. So I would include that. And then
it's not just the silicon, it's also upstream.
Yeah.
So I'm just, every solution is kind of cherry picking different aspects and then coming up with a final system, which is suboptimal. Work through the same problems all the other ones are working through.
But also that ecosystem is dominated by one or two operating systems, right? And there's some choke points, so to speak, that are not present in automotive for sure, right? So there's quite a bit of differences. So we may say there's an example how somebody solved it, but in my mind, it's so remote from automotive that it doesn't really inform me much as to how they, why they did it and how they did it. It doesn't seem to apply as much to our case. I could be mistaken, but it's a very different setup. Hence why even ML Commons have different divisions for different things, right? Like client, server, IoT, and now it's going to be automotive and probably some other ones. So even MLC hasn't, solved it in a universal way. There's some cross-pollination between things, but there's enough differences that you're handling things differently for different setups.
So just looking at the time, Nikolai, there's 20 minutes left before people come back in and get refreshments in this actual room. So it'll be a little bit hard to go long. So I just want to make sure you're aware of that. That's all.
I'm aware, and I actually value a lot the discussions we had. And I don't know if you've seen, but I was adding a few points to the bullets we already had during these discussions to these respective areas. I would suggest I just walk through what we have here, which is things we have gathered before this meeting and things we have learned during this meeting. And is that fine, Stephen? And then we close in a few minutes.
Yeah, I mean, we have 20 minutes. I think that's a good plan. Why don't we go back through review and fill in some gaps? Because, I think to the point, then that will define the scope of future discussions and start building up.
Yeah. So on the stimulus side, we were discussing different kinds of workloads, real workloads, full software stack with or without operating system drivers, test bench stimulus, or there's quite some variety. We have heard references to CPU benchmarks such as Geekbench or SpecInt. Last time we were also mentioning to generalize on operator offloading. Should not be necessarily here the scope, but might be in ML Commons, right? But the size of workload to be of interest, if it can fit in the accelerator, or if there is a data path which spans across multiple hardware compute elements. Then today we added here the system workloads where there's DUT workloads which share resources. So this is a question of how much of the SoC is modeled. And the ARM was mentioning that there is already some kind of combined workloads where eventually one application is executing a real workload on the IP and other system elements just get loaded from a replay of communication or synthetic loading scripts or something to model other aspects there. And then also a general remark that was given is that the automotive workloads were usually characterized by low latency, fixed cadence, and it is relevant for such stimulus to identify the most relevant workloads to maybe not model the very small, very rare memory requests, but focus on those which are defining the performance. That's all I have covered for stimulus so far. Was there anything I have forgotten to add to this list?
I don't know if you, I mean, obviously this is a little bit general. I don't know if this whole boot up topic, if that's a specific kind of stimulus or.
It's you said CUDA for NVIDIA
booting
GPUs,
up,
sorry?
so the boot time.
Oh,
That's a good
actually,
point. Does it follow the stimulus or use case? That's what you have to try and triage.
Yeah, well, sorry, so boot
Or is it a
boot
KPI?
time is a KPI is the time, I guess. I mean, the use case is the booting scenario, but then are there specific stimulus?
So we can reverse cover.
Yeah, yeah.
So, click on.
No, I'm just thinking it's all good info, but I'm just thinking from a deployment strategy from like an OEM or somebody else. Like you said, there's a lot of legacy kind of going from one generation to the next. You redeploy from one SoC to the next, and then you find new constraints, which cause you a lot of pain, right? So if you do the pre-silicon and you really have an A to B comparison and make sure there aren't new constraints in the system, and at least your overall system performance is going to be theoretically better on this pre-silicon benchmark, then at least you alleviate one concern, right? So I think, so that'd be like on the constraint side of it. So if we do this, I'm just thinking they're kind of, some are dabbling their toes in like the AI implementation, but they're not going to throw everything away. It's kind of, I want to slowly migrate over. Yeah, build over. And I want to make sure that whatever I have legacy is still going to deploy and it's still going to deploy efficiently. That's where I think like an A to B comparison on a pre-silicon, it's kind of reducing the pain points and knowing where your constraints are would be kind of a cool, good storyline behind the paper.
And especially tier one, I think Bosch should use it, right?
Yeah.
You guys have been building reverse like systems with infotainment and reversing cameras, which are meant to boot up really fast right now. You wouldn't obviously throw that away. You have learnings from there, and you know how to boot up quickly with the reversing cameras.
Yeah. Until you go to the next SoC and somewhere.
So
But
if you had, so you mean if you had, let's say, a system on a current SoC platform, you would want to benchmark that same system in pre-silicon, both the existing system and the future system.
Yeah, right.
At least make sure you didn't break anything, right?
Yeah, at least there's not any new constraints that you had available.
That's a challenge though, because again, Nikolai, correct me if I'm wrong, but what happens is the EDA environment that you use to build up your previous generation is not the same because your EDA tools kind of evolve, right? And you have newer versions. And you again, it's a challenge, and I think we face this internally within ARM, right? Our older IP was built on certain versions of tools. They were tested and certified on a set of tools which are out of date now. Now, for the new IP, you wouldn't use the older versions. Equally, you wouldn't port the old version to the new IP because that's a lot of effort. That's again another challenge too. Is you can benchmark it in real silicon, but reducing the same environment for their legacy product.
So you know what the design outcome is.
Yes.
And if you use new tools, you use new tools, right? You still know what you're trying to achieve.
But at least you know the target. So you have to trust that the tool is giving you the right answer.
Right.
So if that's the case, then I guess to your point, yeah, you wouldn't have to. The reason why I was thinking of you would apply the tool on the old design is it would verify.
Yeah, I know.
The tool would, it'd be tested.
And it makes perfect sense, right? That's what, it's an absolute desire to do that. Because that's your point of correlation. Because this is what my EDA, when I did the pre-silicon stuff, this is what I got. When I do my, when it reaches silicon, then you do the correlation, right? And then you try and reproduce the same environment with the new generation to get that confidence in your next generation's pre-silicon platform. So you build it. But again, it's possible, but it comes at a cost and it has challenges.
Yeah.
Oh, by the way, Nicola, I just sent you that slide that I was mentioning. I sent it to you via email. Maybe you want to share it with the, copy the picture, share it on the thing, and then remove it if you want. Maybe we can have a discussion around.
Sure, very good idea. Yeah, I will briefly bring this up. I think it's also perfectly matching the topic that we were just discussing.
I actually made this slide months ago, but I put AVCC in there even before I showed up with this conference. I wanted to work with it. So, but that's what we need, right? We need we need to come together, right? We can't solve this in isolation. We need to come together as an industry to help solve this gaping hole. So now so the point of this slide is to show that yes, we can reuse some bits from the client side, yes, we can reuse some bits from the infrastructure side, but there is a gap in between which needs to be filled. Right. So based on the analysis that my team has done, there are workloads inside the client Geekbench suite, like things like mapping, things like image processing, and there are a few others which I have another slide on that, which we can use as representative for IVI and infotainment use cases. Similarly, on the infrastructure side, there are some big data problems or some ML-like workloads which we can somewhat call, if you squint really hard, you can say that, okay, they're kind of similar in the automotive space, but there is a need for something more specific to automotive. And yes, ideally, you would want to use the actual workloads that are in the industry, but for us to be able to just use them, because even if a customer is willing to share their workloads with us, right? Arm's legal team says, no, there's a risk of IP pollution. We will under no circumstance let you get this customer use application source code into Arm. So that's why we need something which is more industry standard, a bit more generic, preferably open source that everyone can use it.
I see. Because if it's an open source, then there's no IP.
Then there's no IP pollution risk. Yeah, that everyone can.
So if AVCC had a whatever open source.
And that's probably the perfect segue into the system benchmarking, which is also very interesting. Yeah. Unfortunately, the session is a bit too late for German timing, so I won't be able to join today. But I'd like to follow up on this topic definitely.
It's never too late.
Depends on when you woke up, exactly.
And he put his baby to bed several hours ago, and it's time for him to go himself.
Before the baby wakes up in an hour.
I woke up at 5 a.m. today because I'm still on UK time. So I had a very late morning with my UK standards.
Up at 5, but
so just to finish our summary of what we were also discussing was on the design under test side, we were discussing to really identify those elements influencing the KPIs and define the fidelity or accuracy we need for each of these elements that are defining their. We were discussing different models. There was mentioned RTL implementations on FPGA as an example versus System C/architecture models. There was ARM fast models listed here. So those might be used for different purposes, and some might be performance targeted. Maybe I add this here, performance targeted, and the others fast models might be more accuracy targeted. Then also we're discussing that there might be different time scales if you want to mix and match those systems. Where this is actually related to the topic above, on the system environment, to identify those most relevant elements. As an example here, an NPU plus interconnect plus memory, whereas the rest is only modeled via memory accesses. And then we also had here for RTL benchmarks, just a side note that if you run those in simulation or emulation, obviously this will influence the wall clock time you need to run those benchmarks pre-silicon, but this should not have an effect on the measurements, on the accuracy, right? Whereas choosing the model has a tremendous effect on what you actually measure.
The methodology should not let that difference affect the KPI. I think that's the important thing. You need to have a methodology that is resilient to that being a factor. Right?
Or at least I think it's a good point that you say it shouldn't. I think at least it should be defined what accuracy you want to achieve, right? Like if you're fine with knowing it plus minus 20%, maybe it's up to you which or maybe you have different options to choose from the DOT implementation. Yeah. So this this is a very valuable point. Yeah.
It was not my point, but we haven't captured that, but that is also a very good point what you mentioned. Because yeah, we might be, for example, memory controllers is a good example, right? Do you care about how far down the system do you care about your, say, memory controller? Do you, because that can have an impact on performance, but you say, okay, I have an idealized memory controller and that's going to give me single digits performance variance. I'm not going to drive myself crazy by having a real memory controller implemented. But if you did care about the memory controller performance, because it will matter for your real-time performance, for example, right? Even a few cycles can make a difference. So you may want to implement the real memory controller IP and have cycle-accurate memory controllers as well. You can program idealized memory controllers to have certain response times, but again, it's idealized. So
yeah,
right. And I think
fully agree.
It's good to maybe capture that whole trade-off between accuracy and runtime or estimation time or simulation time. I'm just thinking again in terms of the actual document, right? A section that describes the tools a little bit, and for those that aren't.
The other thing was, again, one of the challenges is getting access to these pre-silicon platforms. And I'm looking at the Siemens guys in the room, to fix that. Again, it takes significant investment from ARM to bring up an FPGA system. It's not something which everyone can afford. It's even within ARM, we have to fight over it, and it's a shared resource, and it takes a lot of management.
They here, so.
Yeah.
AMD is happy to provide more.
Exactly.
Yeah, you can fix that as well. Sorry, man.
That's low bound.
Yeah. That's why they bring wide. It's like the share. No one's looking at it, but yes. But no, if we can enable FPGA platforms that are more, I guess, easily accessible, or
like a cloud service, or
you said it, yeah, the cloud service which you can get some time on and just run your workload, and you get.
Well, that's something we should talk about.
Absolutely.
I mean,
it's yes.
I mean, it's outside of automotive. It's funny because it's outside of automotive. Certainly part of it. Focus.
Yeah.
And this is what you mentioned is a very important point, and I think it's somehow related to pre-silicon, but going into a future roadmap. So I would love to have a side discussion with you on that. I think there is something we already are doing in that direction. Yeah, that maybe you should be made aware of. Yeah.
No, I'm well aware. I'm just making that problem visible to everyone in this space. Right?
Yeah.
So that's my intention.
Maybe just one other topic to capture. I don't know if we want to address it. Is kind of going back to the whole chiplet thing. You have a chiplet and doing it's not a well, it'd be the system benchmark. So if you have one new chiplet you're adding to an existing system, then you want to benchmark that. There might be some different, might be different than how we do it for PCs, because you'd already have measured values for everything else.
Yeah.
You'd have the UCIe interface.
That's right. I'm just think, I hadn't thought about that, but again, but that would be just the question of replaying. You don't even have to run the software. You have whatever transaction, you just maybe capture them and replay it on the bus on the UCIe interface, and that's everything modeled for you. It's just at the transaction level. Maybe that's a shortcut you can take, and that improves your experience as a performance analysis.
You need that for chiplet, right? You want to add a new MPU or something.
Okay, very good. And I think last week we were discussing KPIs. Several times it was mentioned performance with respect to latency and throughput, which could be an algorithm latency, throughput, communication latency. There was a mentioned in the past to have statistics, including variance of latency, like worst case, average case, and so on. And the influence of different elements on latency, maybe even having this as an option to break down which element is contributing to such a KPI in what matter. It was mentioned to have power. There we were in the past discussing about having approximated power only based on like a average toggling rate, or if you actually get accurate power results from running real traces through a post mapping after cell synthesis tool and get very, very accurate numbers. So also this is a trade-off which we captured above, which we should cover, like accuracy versus simulation time of running that, right? If you need just approximated numbers which you can compare relative to each other, or if you actually need absolute numbers, relative comparisons versus absolute numbers. And then one big topic was always area, like a silicon area, influencing that, and which might be technology node, or should be technologies node specific, or also here relative numbers versus absolute numbers. And then also in the past, we have seen that different companies capture different elements under the IP area. Like I have seen a company stating our IP is very small, but it requires a certain local SRAM memory size, which we did not include in our area or not. So that should be covered in the report. Today, we also learned about other KPIs, such as freedom of interference, quality of service, and then real-time analysis, which we should dive deeper in the next working group sessions. And also that there is needs to be some way to respect headroom for future updates. So don't have 100% utilization in the beginning, something like that. However, to discuss how this could be covered in these KPIs in one of these next working group sessions. With that, I don't see currently any hand raised, and we're exactly on the minute. I see Stephen. I very much appreciate all the valuable contributions during these 2 hours on pre-silicon. I think everybody is invited for our subsequent working group meetings. We will have those in a bi-weekly cadence on the Wednesday, so not every week, but having them bi-weekly interleaved with the system benchmarking. All details from the AVCC team, and everybody is warmly welcome to join this and yeah, further detail our guidelines here.
Yeah, thanks, Nikolai. So people are already poking their head in to see if we happen to be in the room with the refreshments, so we'd offer you some, but good, perfect timing. And thanks, for leading the session. And I thought it was very interesting. So
thank you.
Thanks a lot.
Right, bye. We'll hang up from this end too.
Gute Nacht.
We'll be back on 30 minutes for those who are available.
Who's ready?
Yeah.
I'll hand it back over to Stephen for benchmarks.
Yes.
Oh,
That's fine.
sorry.
Yeah, so what we'll do is continue the system benchmark. I think what we did before was mostly set at this table. So if you want to join the discussion, make your way over here. We do have a camera pointing this way. And then for anyone online, please join. We'll give it another minute for people to join again who are on. All right, so for the system level benchmark meeting, so Ramesh is back. I don't see anyone new. But what I'd like to do, Austin, I don't know if you want to come over closer or. I'm gonna just basically use my laptop as a way to take notes. And what we want to do is try to cover what it would be for a system level benchmark. So obviously what we did is, as many of you know, Casper Mecklenburg is the chair of this working group. He works for ARM. He's done a fantastic job. We've gotten 3 technical reports out of the benchmarking working group. Those technical reports were the basis of those technical reports were the basis for the collaboration with ML Commons on the ML Perf Automotive benchmark, and so that's really been good. But now and those were all basically focused on the perception and deep learning tasks. So now we're saying, okay, for benchmarking now that we have this actually building a benchmark with ML Commons, we don't need to keep focusing on that area. What else can we do? So earlier we had the pre-silicon benchmarking. So that's one direction that we're heading in. And then the other direction that we want to head in as well is system level benchmarks, not just the AI part of it. So the goal for a system level benchmark, I think, has been in AVCC, as I understand it, for a very long time, but not something that we've achieved. So what I'm going to do here is basically we'll lead a discussion, and the topics will be as follows. First, we can talk a little bit about the purpose of the system level benchmark, what we're trying to achieve, then how we define what a system is, the scope of what the benchmark would have, some of the steps to achieve the benchmark, then maybe specifically what that goals or output of the work would be. I'm going to close on this side the chat piece. All right, and I see we have Isaias joining. Hi, Isaias. There's maybe, I would say, 10 of us in the room as part of the discussion. We all were introducing ourselves in a previous part of the meeting on pre-silicon benchmark. you want to just give a quick introduction of yourself? Oh, we don't hear, hold on one second, we don't have audio.
Might be on mute.
Are you on mute?
I can see on that. Okay, now is it better?
Yeah, we got it.
Okay, yeah, it was my setup. So hello, my name is Isaiah Spech. I am located in Detroit. I work for Stellantis and I am in the AI/ADAS team. Nice to meet everybody.
Right, maybe we'll just, why don't we just quickly say your name and your company? I know not everyone was here before, but Stephen Miller, Bosch, and Technical Chair for AVCC.
Michael Meyer, Bosch, Technical Project Director.
John Correntis, ARM. We got go-to-market activities. Building AVCC.
Masahiro from Denso, the Director of the Technical Development, Engineering Development and Promotion Division.
Umair Hashim, Automotive Law at ARM, and I performance analysis team within the automotive law.
Neil Banerjee, AVCC, as well as VP from Vista.
I'm Mark Singer from XL4. I also head one of the work groups of the eSync Alliance.
I'm Paul Zarati from AMD, an automotive system architect.
Ali from Aura Intelligent Systems, a startup company developing radar.
Rohit Arya from Bosch and part of the cross-domain computing and advanced engineering.
Austin Bailey, Bosch, product management, ADAS and cockpit HPCs.
And we have a few additional online, so yeah, please, I think Ramesh was on before and Predrag, but please say hello.
Yeah. Hello there. This is Ramesh Anawajala. I'm from Blue Fusion. We are a sensor fusion solution company from Boston.
Predrag Đurđević, autonomous system design engineer, ARM.
And one other person online. Okay, well, we will go ahead and get started. Yeah, thanks everyone for joining. We're set up in a big room, and the just so you know, the video camera is capturing just one of basically 2 tables worth of people, but hopefully the audio works for everyone. And then we're also displaying it on the screen here behind me, so we'll see us facing the screen. That's what we're looking at. Why don't we start out with the purpose of system level benchmark, and what we'll do is maybe I'll talk through this, and if we have some additional, let's say, content, then we'll fill it. We'll add to that. But then once we get past this slide, we'll start talking what should be in a system level benchmark and what would it be. The one way we're looking at it is who's using the benchmark. So that's the customer who wants to use the benchmark in some way. And obviously the big one, if you're trying to build an ADAS system, is getting the right size of the SoC and the right amount of memory. At some point you need to specify that in RFI, RFQ. And this is also obviously a major component cost. Picking the right SoC is a major component cost, both from a piece price, element, but also even the tools in the ecosystem and the software that goes along with that. If you're the SoC supplier, then you can actually give a performance number based on, an industry accepted benchmark. So that's, obviously really helpful, but it also has a way for the industry to tell the SoC suppliers what they need. So then the right SoCs, the right chips can be developed, the right roadmap can be put out there. And then broadly speaking, this what we say for the ecosystem, when you have a target to achieve, then that actually spurs development, right? Especially if you're like it's like your stretch goal, or your performance target individually. If it's a good one, it actually, it helps you to get there. And that happens, I think, at an industry-wide level as well. And in terms of what we want to do, and we'll get more into this, generally, what is in the system, level benchmark. And, in terms of memory, compute, their safety, what are the tools and data sets you need for a benchmark? And then how is also that benchmark sustained over time, right? So not just one piece of software and then kind of dies. Maybe I'll just pause here then. This is meant to be an interactive session, not a presentation. Are there other uses or views of system level benchmark that we should capture here? Neil, go ahead.
I have a lot of feedback, but before I start rambling, maybe anybody else has worked on it from a customer viewpoint. It's not as simple as this. I have my own, data input that I can give for the team. If anybody else has any other feedback, please go ahead. Otherwise, I'll
no, go ahead. Go ahead. We have like an hour and a half here. So,
okay. So from the overall perspective of customer, because I went through 2 different launching vehicles, developing. In those, my experience has been that the engineering has taken the lead in defining the product or the suppliers and everybody. Tool sets, everything. Purchasing was just involved to make their, whatever they want to do with money. That being said, when as a overall OEM, whenever we start talking on ADAS functionalities. We start with functionalities, and each function comes down to individual use case and performance target numbers. And those target numbers are not very simple to calculate, because I cannot say my braking has to be 3 meters per second squared just for the heck of it. It all depends on the vehicle size, the weight, the whole, how is it SUV versus small vehicle. So when I'm talking about the overall customer view, a benchmark level where I haven't seen any as of now is that feature sets. For example, what is a good benchmark data for AEB? Nobody can give me. I was hunting for it.
What is AEB?
Automated emergency braking. So give me, like when I ask a tier 1, sorry, forget about tier 1. I'm going to ask a supplier, it all differs at this condition, that condition, this X, that Y, and then there's no right answer, right? But there is a good view of why they cannot give, because the whole environmental factors, the whole vehicle dynamics, the selection of, say, powertrain, chassis, everything comes into play in defining a kind of a number. So I would say it would be really useful from, say, OEM perspective, if we can develop a set of good benchmark, say, we know what are the level 2 features there, what are the European homologation requirement for those features, or say for US is FMVSS 111 only now. And other OEMs have said that we will launch AEB. It's not mandated, but they have unwritten. So if we can develop that as a guidance, we can never say this that number, but based on this, this is where the range of performance number comes out to be. That would be really helpful for the OEMs to basically consume that data. But they will make their own analysis, but at least it's a good start.
So in this case, the regulation is catching up, right, with the Euro NCAP standard?
Yeah, but Euro NCAP is also another different thing. They give a kind of a very top level view of the percentage of the categories with a score. But how you come to the score is on you. You just use it as a kind of input, but that does not define, because under AEB, they may say, okay, this, but underneath it for an OEM, AEB, the total number of performance or benchmark data that they look for is like has 150 other subline items internally. So those are the kind of categories which I feel. And if you guys need my input, I can give you those subcategories as from my own experience. But I think that would be really amazing work, which I haven't seen anywhere. It has been since 2018 on 2 different rated programs. I haven't seen anybody do.
So what would it take to do that? Obviously, you said the actual performance is so condition dependent, right? Would it be about, okay, how many times can I sample and actuate? What is the frequency of that? Or,
yeah,
you know,
for example,
how quickly can I consume the sensor data and put out?
Say for an example, let me say in camera in a snowy condition, how much should be the lumens that's reflecting or whatever you can come up, as a kind of an input from others as well and see or simulate. You can use simulation also, the kind of a good pickup.
But when it comes to the braking performance versus the sensing performance, it's different, right? Because
that's what I'm saying. It's a why I say it's not that simple.
And the legacy systems are somewhat like the brake controller is the arbitrator. No matter who gives a request for a braking request, the brake controller is the ASLD system that's going to arbitrate and decide whether I'm going to apply brakes or not, right? So
no, that's what I'm saying. If you want to see the added value from an OEM perspective, I'm giving you my feedback based on my personal experience. What added value, if I look at data like that, oh my God, it's a goldmine.
So Stephen, when we call this word system, is it system as an ECU or system as a whole vehicle? Looking back to the scenario of braking.
Yeah, it's a
compute system. It's a whole.
It's a whole.
Yeah,
I would also define vehicle.
Well, I mean, even
system as
that's. Go ahead.
System of systems is the set of controllers which are based on different architecture, right? Going all the way to the silicon, right? So pre-silicon. That's how we are trying to go.
I think Predrag had a comment as well.
Yeah, I was about to say, I mean, the context of automatic braking has nuances there. So NCAP actually has some scenarios that they're describing pretty precisely, right? As to, you know, what is the setup and has to brake, there's a pedestrian and so forth. That's not all, of course. You have either, you know, linear braking where you're not really evading anything. You have braking with steering actuation where you're actually avoiding things. And it gets even more complicated depending on, do you have lanes on the side, they're in a highway, do you have cars left and right, and so forth. So, of course, it depends on the context, at least the perceptual prediction and planning part. Once you get to actuation, where you already know what you need to do, then it's more repeatable and more definable, right? Because if this is the exact trajectory I need to follow, then it's easier to do that part in a more controlled way because there's not that much variability other than the road surface itself, right? But when you're backing to the perception, prediction, planning, of course, it's going to depend on very small nuances in the scenario, right? Some small things can balloon into very big things in terms of, you know, performance.
My observation, in part driven off of the definition of system shown here, from my experience, the more layers are present, the greater the potential for variance off of whatever you try to set as a number, to the point where, and I'll use some numbers just by example and don't worry about what the use case was, but from an actual conversation, asked to give numbers, express some hesitation, you got to give us something. Okay, could be a base of 25K, and depending on how the layers are built, that's 25K plus or minus 40 meg. But typical is 75K. You could build it up to 40 meg. Starts at 25, typical is 75, you could build it up to 40. The variance between what I described as typical and what you might find yourself with is not just percent, it's not even just multiples, it's multiple orders of magnitude.
Yeah.
And that's the scale of range you're likely to see when you have such a complex stack as this. But it still could be useful to articulate it in terms of base, range, and typical. Because you're not going to get one number that has any meaning.
I think that's what I'm saying is that, you know, from your OEM perspective, it's really confusing because they get bombed from different PowerPoint presentations from different suppliers, and it becomes very confusing. If you want to have an added value from an OEM perspective, the customer view, I would say that's where would be a real good work. And it's not going to be that easy. So that's going to be a real tough one, but it's a good problem to work on.
SAE levels, you know, ADAS levels, a good way of compartmentalizing the
feature sets,
the complexity there, or
SAE go with the homologation. So pretty much fine.
Yeah.
The problem is you have so much range in each level, right? If you just look at L2, that can range both in terms of capability and therefore tops and T-flops numbers tremendously, right? Several times. And L3 and L4, right? Depending on what you're handling in terms of the ODDs, right? You can claim L4 and be very geofenced or do some, you know, very, very smaller section of things than you know, entire world like in L5. So anything that is associated with SAE levels is a little bit relative as well, because these levels are pretty broad in terms of what they internally do, you know, both how they're defined and what they can internally do in a specific instance. Plus, we have L2++ nowadays. Steven just
actually plus
series.
Yeah, I missed one.
Yeah, but if you look at
What time does it become L3 minus?
No, L3 minus Mercedes, what the special area, you know.
So Paul had a question.
I was just gonna say, I mean, one of the things that AVCC can do is to help define. I mean, I don't know if SAE has taken that on, right? I mean, they're the ones that started these different levels. But it's so frustrating to me that when somebody, you know, and I mean, we'll get an OEM RFQ and they'll say L2+ features.
Yeah.
But I can't define it, right? So what is the sensor set? What is the? Exactly. So just something that we can base a discussion on is of high value.
It's simple, right? Anything above L2 and below L3.
No. I think for this, I don't know if it really matters so much. You're looking at how many sensors you're processing data from. You're looking at the overall response time of the system, and you might have different requirements from a safety standpoint, but otherwise it's.
I agree, but some of the times they won't give us the sensors. They won't give us the sensors. So I know.
Do they at least have a breakdown of feature set, like say AEB or
No,
steering?
and that's really what would be very helpful from what does L2+ mean? Oh, okay. L2+ means, is it highway pilot or is it urban driving? Because those or is it both?
Because it could be like, say there are 4 features that define L2+, and we can choose 2 of them and still be L2+, or 3 of them that's still L2+.
Yeah.
Or 1 of them that's still L2+. So maybe we have that.
I still don't think it's. Really, I think depending on which features you want to implement, you might have 20 sensors, and it might not be an L2+ system.
Yeah,
right?
I agree.
And that's
the sense
I was trying to say. And that's what I mean.
There's good. It's an implementation choice, the number of sensors you use to. It's about enabling a certain functionality. You may be able to do it with 1 camera or 10 cameras or camera plus radar or camera plus ultrasonic sensors. I don't know.
But it's more of a scaling based on market trend and availability at the sensor side.
Well, that's the fact that target is moving. DMS tomorrow is not DMS today.
Right, exactly. And that's where I think it's more on what's kind of from a market standpoint. If you look at cameras, for instance, you have a camera today, you might look, you benchmark a car outside and say, all right, I got a 1 megapixel camera. You're not going to have a 1 megapixel camera now. And I think when we had those presentations at the beginning, AVCC, they were pretty transparent also from GM and Toyota to scaling from the camera standpoint, where they want to go to. And I think it's just generally based what's available in the market. And what do you see as far as just completing the market?
Yeah. The only reason I say it because it's something that I can view as being helpful.
Yeah. But I think you maybe break it, but it's really just the scaling on the sensors sitting here.
I think somebody mentioned on the call the homologation features that's mandatory now in Europe, and also the NCAP, and also the US FMVSS numbers. If we can target those and work on it, that would be a great start. You know,
that's work actually in defining.
No, it's already there.
No, what it means for AVCC's point of view. Maybe we have an opinion to say that, okay, when we say L2 plus, it can mean these things. And
nobody
just said it corresponds.
No, instead of targeting whatever, OEMs always know what does L2 mean and what does plus plus mean on marketing terms, right? They do parking, add on parking feature as a plus 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 added like that. But if you target those features as an NCAP, that's an immediate win for them. That those, oh, okay, I see this is mandatory required to certify my car, right?
I can sell my car.
Yeah, that's what it's an immediate win. And I find that would be a really good, we have enough brain capital in this room with the experience of different things. So we can definitely do it as a kind of a good work group. I feel that's as a customer.
Yeah, then
what I feel here, this point is completely valid versus that on the screen he's talking about the system. So either we take it together or maybe we take it separate, but this point is really valid to document it.
Yeah.
There's L2 versus AEB, right? There's two different topics. I believe AEB is still L1.
Yeah,
this is an example.
You can do with 20 sensors, or amazing company like, she's developing can be done with one sensor.
Yeah.
So who cares?
And
right?
L3, AEB is always there, right?
Yeah.
AEB is still there in L1, L2, L3. The safety features governance going to bring, it is not about L3. It's more about what makes it safe. And that is AEB or driver attention and all that. Right?
So
everything else is marketing.
Yes. Yeah. So I'll give you my personal experience. I was talking to NHTSA auditors. When they were reviewing, there was some issue because they really hate this kind of L2. What is your system? If I say L2, what is L2? I don't care. Tell me about this feature, how it is that. They themselves don't want to use those terms L2, L2 plus. This has become so fragmented now that nobody cares anymore. Okay, feature wise. They're targeting only the name of the feature. Okay, this is there. Okay, how it is done. So if I go through these auditors also from NHTSA, they themselves, what are the safety features you have implemented? Right? And those are the kind of thing I think becomes much more important.
So just the feature become like the micro benchmark.
Yeah, the feature becomes a benchmark than the levels.
But the scale would be coming with the sensor set.
Yeah.
So,
but for the purposes of this exercise, we're seeking presumably to build a set of blocks that you would put together to get to what's described here as a system level benchmark. But do they simply add or not? So if I have, 3 different features that each have a typical benchmark requirement or typical benchmark consumption of resource, if I add all 3 together, what am I going to get? am I going to be deceived by saying, oh, that's 3 + 8 + 4? So therefore, I come to some conclusion from the numbers that I saw, and that conclusion may be entirely misguided. So we have
referring to
Yes,
sensors or models by adding, when you're saying adding things, can you?
You're not going to run 5 instantiations of your perception, though. You're going to
Right.
run one. But that's why I think it goes to your scaling. Then you have some constraints from like a regulatory thing. So I still think if you're maybe defining your overall latency based on regulatory standpoint, and you look at the scale, then you can actually maybe look at this is how I frame it up from a system standpoint.
Can we not abstract the sensors, the number of sensors, the types of sensors out from the feature set?
We could.
Yeah.
And that might be a good way to, where you expect that, okay, I'm gonna do whatever I need to do with sensor fusion to create this data set. How you get to that is into the cameras or whatever combination of sensors. But this is my core use case.
The interesting part is for low speed. Sometimes you can achieve the same result with simple ultrasonics analysis. You don't need the radar too.
Doing obstacle detection.
For example, actually, yeah.
Right,
Well,
but
I mean,
that's a
the
solution.
feature set describes the aspirational thing that it can do, right? That promises can do. Where the scaling goes is if you discount for sensors is basically what's the reliability of it, right? You know, how 99 point how many percentage can it achieve that, right? With those margins. So that will scale the entire thing, that being the reliability of it will scale, even if you fix the sensors, because you may need to add more models, you may need to make models bigger, you may need to add some other redundancy models. So there's all sorts of things that will basically need to be scaled to achieve not just the feature set, but actually promise reliability of it.
And as you said, right, the speed matters as well. At what point does that feature kick in, and where can it operate? Is it a different feature set?
Like speed or low speed?
How high can the speed be? It may be able to do it within 40 miles and not at 70 miles or higher than that.
Yeah, but I don't know if you need to worry about that.
Right.
For benchmark, right, you need a representative set. You don't need
You need
all.
Yeah, and now are we talking about
that's true.
safety features?
The answer of the benchmark will tell you how responsive it can be, what speeds it can tolerate.
Yeah.
How fast is it run?
How fast you can process X amount of data.
X amount.
Right.
That's
I
right.
think that the more critical data would be the safety features, as you mentioned, in safety or comfort.
Yeah.
Because the important thing is the safety features are required to get certification to sell the car. Comfort features are add-on for dollar amounts.
Right.
You still want a reasonable response, otherwise they won't buy your car either.
But or it's worse with the break, you can sue the company to say, oh, you offered this feature, but it didn't.
No, but I think just from a simplification standpoint, process X amount of data, and then you need a certain overall system response to be.
So
Well, if you define all that, then I agree with what you're saying. You can define the sensor set of, where they're coming in, how many cops you need, how many safety units you need versus non-safety. What you're controlling actuators, what you're displaying for the driver. Yeah, then you don't need to describe it. You don't even need to tell them.
You need to know what's being displayed to the driver or what's being actuated from a brake actuator.
Part of the SOC's job is to create the visualization. And I strongly believe that the winner in L3 and L4 is going to be the system that makes the occupant feel the most comfortable. You've ridden in automated driving cars, right? What makes you feel comfortable? I like looking at that screen and seeing that the system knows that that guy's about to walk off the curb and he's going to handle it.
What's not most so critical, right? It's maybe the response system.
Yeah.
And the fact that you will display it, and the fact that you send a response to an actuator, and that you have some sort of safety mechanism in your system where you can.
The visualization is not part of the safety, so it's more about.
No, actually,
It's more about the customer accessory, but it's still a requirement of the SOC to support it.
So some HMIs safety.
It's a requirement,
The
but it's not at the
visualization
same safety level, right?
The requirement because
It's QM, it's not the ASLD type.
it's not looking at
safety
it.
level.
And you can see that way. In an L2 system, you are still the driver. You have to see what is happening.
Yeah, but I'm.
L3 you don't.
L4, you may not have to.
L3 you're still sitting.
Yeah, but you don't have to watch.
You don't have to watch.
Yeah. Allow me to ask one question, if I may. When we use the word benchmark, there are two implicit potential interpretations of the term. A benchmark could be a measure that we get from different implementations to compare them. So how did you do on this? You know, how many tops do you have? Tops would be a benchmark. Versus a benchmark could be a use case archetype. Here's the benchmark value. And then you might compare other things to the benchmark. So these are two different ways of using the same term. And to me, as I listen to what's being described here, I kind of see both being mixed together, and I'm not sure whether we're talking about an archetype that we want to measure ourselves against, or the metric we want to use to score whatever it is that is being done in different places.
So on option 1, I think it makes sense to first finalize the sensor set, maybe have few combinations, especially since the question of TOPS and GPU and sync. I mean, it all depends on how much data you're getting in to decide how much CPU need or GPU need. Yeah. If you don't know how many cameras, and if you don't know what are the megapixels, and then how many parallel items you are going to classify in that, you cannot decide how many TOPS you do. So this need to be documented as.
I'm sorry, I don't mean to interrupt you, but even back up, I need to know how much I'm going, how many C5 pins, what do I need in terms of memory bandwidth just to ingest the data, let alone process it? Sorry.
But then it goes back to number of sensors, right? That is where everything is starting.
Yes.
Like on an ADAS issue, I come from cockpit, but if you look at ADAS, you have all the sensors on one side and all these, whether connected all the DC devices or the CAN or Ethernet or LiDAR, the radar. And then if you see, you have 5 cameras and whatever, right? You know how many interfaces you need. And based on the camera's megapixel, you know how much data is going to come through the devices. Then you can easily decide you need to connect a 4-line CSI or you need to do, or you do a quad, right? You can decide that there. So without knowing the sensor set, you cannot benchmark the CPU scale. Or without at least knowing what is expected in future with that in that car. Like you might be a 3 megapixel, like you are looking at 5, right? Or 8 next year. So we need to start there. And then draw this combination. Scenario 1, maybe premium or high end, like 10 cameras, whatever cameras, how many radars, LiDAR, and this is the range. And on radar and LiDAR, are you passing the raw data or are you passing object or even point cloud? All these impacts the final SOC need, right? So that should be one scenario, premium, high, then mid, low. And that should be a benchmark point on the hardware point. And on the software, I think whatever we discussed, feature might be an option when we start. Safety.
So, sorry, on your time and place, what is the interval? Is it NFD? Is it 100 megabit Ethernet? Is it 1 gig? Is it 2.5 gig? Yeah. Because that's going to impact your CPU too, in terms of servicing all of those.
So I'm coming back to Stephen's initial slide deck about that part with the customer feedback, which is very much using, they use those kind of data to do RFI, RFQ, right? Yeah. So for example, as I said, I had 2 different, like there was nothing, I had to create a RFI. I'm just stating some numbers. And if you guys can tell me if that is right or wrong, let me know. Just two examples. Okay. So I had to create ACC target following flat road. I'm not even talking about the gradients. Okay. I had 3 different categories that has to be done. So at steady state time gap deviation, I created a number plus or minus 0.2 seconds. Then the other one was max approaching speed for stationary target, 80 kph. Then the third one was bumper to bumper distance deviation at stop, plus or minus 1 meters. If I do this, if I give you any one of it, right, this has to, as a tier 1, suppose I give an RFI, you have to achieve this. You will come back and ask me, okay, that's good, but what about the other systems? Braking is involved, right? Will they be able to achieve? Or somewhat, sometimes steering has to be involved as well. So if I give this number, say my RFI, I as a person writing an RFI with these numbers, do I know what I'm talking about? First of all, that's my question myself to me. Is this the right number I'm putting? Where did I come from? These numbers, right? These are the questions that is very much the purchasing department ask the engineering department, hey, you have to create this RFI, we have to send it out to the global, all this. And now immediately, where are all these numbers coming from? You ask me, right? Purchasing will not ask, oh, you are the person, you are the end responsible. So you are giving me, I'll try to get the suppliers who can. Now I'm the end responsible. Did I write the right thing? I don't know.
Just real quick, there's some questions in the chat. I don't know the answer to your question, Theo, but let me just go to the chat because there were some questions from there. And Ramesh, I don't know if you had a few. I don't know if you want to just ask them questions about the sensor sets.
Yes, absolutely. I think there are a lot of questions here, right? First of all, we had a very interesting discussion about L2/L2++, right? It is right now a marketing term, but then it has serious consequences to everybody on the road. The drivers, the people who are not driving versus the OEMs and the government, right? I think this is essentially kind of going back to L2++. That's kind of first question. The second question actually, so my concern actually that I'm really trying to understand whether the industry has come together to define a minimum required sensor, the minimum required number of sensors, like you can define whatever the sensor suite is for, let us say, L2. Versus now, there is a very interesting question about how do you actually benchmark this when you don't even know how many sensors are required, right? Because that's a huge compute problem. So that then the question will be that does it make sense to actually kind of over provision the system and then unlock the capabilities over time so that at least you now have a well-defined workload from a benchmarking standpoint. The next question is a little bit more, it's really not provocative, but it's more like our day-to-day realities of living in East Coast. Like, we are in Boston and it's not winter yet. I actually, dropped a picture that I got from NPR a couple of years ago. So these are the winter conditions where you don't even get to see the lanes. The camera doesn't work. We all know that, right? You cannot see the lane marking. The lane detection algorithm doesn't work. Then how do we actually, kind of understand this real problem?
Well, the camera doesn't see the lanes, but if it knows what the map is, it can actually see other things. So you don't rely on the lanes all the time.
You have the IMU. That is what the IMU for.
HD.
Yes, guys. I think generally, if you look at the picture that I put it right in the Teams, you can clearly see that yes, a human being can actually see what's going on. Right, there is a person walking across, and you have the red lights, and you kind of see a snow-covered detour. You definitely cannot see clearly, confidently the green, basically the road, the name on the green thing, right? We definitely don't see this, these lanes. Yes, you can now add a GPS, you can add an IMU, you can really make it like a very expensive solution. But then the question is that there is a driver in the car. That's the ADAS model.
Well, GPS is not that expensive. IMU is not that expensive either.
Correct. Yeah, no. I think I generally agree at that point. Actually, I think what we're really trying to ask is that do we actually have those things also covered here as part of the benchmark? Are we only talking about AI ML models from the vision?
So maybe just, I mean, I do want to try to get us back on the benchmark topic a little bit. And I think your question, yeah, I mean, the answer is it's not just the vision for a system level benchmark. I think most of the discussion right now has been on the fact that we prefer sensors over specification over the words level 2 or level 2+. Isaias, you had a question as well, right, about how the autonomy levels map to the sensor suite. I will just say briefly, the image here is from the very first technical report that AVCC put together, trying to basically answer that question. But maybe if you wanted to comment on any of this, Isaias, or elaborate.
Yeah, sorry, I missed that picture. That makes sense. I wanted to, because I saw we were talking about L2, L2 plus, L3, L4, which there are 4 levels, but I was looking at 5 sensor suites, so I wanted to see what was the mapping before that. I also agree with the previous comments on, yes, we need to kind of define the features which are going to be part of these levels of autonomy. But in the end, I think the importance is to have, for a system level benchmark, it's about what sensors we're going to use, and then the algorithms are going to be used, right, to assess memory bandwidth, also TOPS usage, GPU usage, ISP, right? So I agree that defining the features is important, but at the end, we want to be able to compare apples to apples, all of the different SoCs with the same. And I agree that every single OEM, I assume, will have a slightly different approach to the levels and approach to the features. But at the end, the important is, okay, what model was it executed from the perception stack? What was the pre-processing done on that camera, right? And what is the and based on that, get a feeling for what is looking at, right? At the end, if we have a standard benchmark, it needs to be generic enough for multiple OEMs to use it. And unfortunately, because of that, it won't be exactly the same for every single OEM. Does that make sense?
I think the benchmark has to be narrow enough. I mean, for different OEMs to be able to participate, right? So something that's controllable, like what we mentioned earlier, the NCAP braking, scenario with avoidance or something like that. So something that's relatively well defined in terms of input output that you can measure repeated with a little bit of variance, right? When you start dictating what algorithm someone's going to use, that's where things get a little bit problematic, because different accelerators, if you will, are suited for different models or different, types of, approaches, if you will, in terms of more classical versus more modern, inference and stuff. So you need to be careful there as well, not to over define, if you will, what exact algorithm. This is not Geekbench and other stuff. I mean, it doesn't fit that same mold, at least not in my mind.
I do want to maybe come back to the slide you sort of quickly skipped over, which is defining what we want to include in the system for system benchmarking. Would not be the full vehicle, because for testing, we don't have a full vehicle to test or a full vehicle model. So I would say it's the compute system. Compute, of course, could be a zonal architecture, it could be just an SoC, it could be just an ECU. We can discuss that. I did want to, and we've kind of already discussed this, I did want to go through this a little bit though, and just say, and maybe for the purposes of this discussion, let's say we'll cover kind of an NCAP safety level. We'll do something that I would call level 2 hands-free, roughly, because we think that's probably going to be pretty broadly in the market. And then maybe let's call it somewhere level 3, level 4, if we wanted to have three things, and you have to interpolate between the rest. In terms of sensor sets, maybe some feedback on what we would want for that. And do we actually want sensors, or do you just need sensor data?
Do you want to call it sensor, or do you want to call it IO? Because
IO,
I think, is that kind of
At the end of the day, that's what we're trying to deal with, right? It's not just peripherals. So like, for example, in compute terms, right?
Yeah.
Amount of peripherals that your compute can handle with the load. In that way,
or high throughput peripherals.
yeah. Other way.
In the automotive world, we prefer sensors.
Sensors would preferable if you're talking about the external sensing. You have all sorts of internal I/O that's not related to kind of external sensing of the environment, right? So I would leave the I/O for those other usages, if possible.
So you want to, you're suggesting we have that captured separately, sensors, and then a separate item as I/O?
Yeah, that's important, right? For sensors, everybody knows what sensors are, right? I mean, unless we're talking about, drivetrain and those types of things. But in autonomy, we kind of know what we're talking about in terms of external sensors. And then you could maybe bundle this other stuff that is more internalized into I/O, or however you want to use it as a word.
It's a great question. Do we want to include, so far we have been talking about reliability, safety, reliability. We want to include availability of the feature as part of it. Like availability means if you're working only with a camera-based system, you might not be able to turn on the feature sometime when it's raining or snowing. Whereas if you have a LiDAR or radar, you might have some extra chances to turn on it.
But I think that becomes the OEM's responsibility for fail-safe. For example, why they use so many multiple sensors is basically sensor fusion is if one of them is not working, the other becomes the priority, right? So whichever data is strong enough, that would be used for detection.
Right, that is when you already started it and rain starts, right? You are driving with this feature on and then it's rain.
Then the camera is not there, then you have the radar that's becoming your primary.
What I was trying to tell you is the previous step. When you are about to start the feature and it's already raining, you are not, some of the cars doesn't.
But there is a feature check already done.
Right, so you don't get the feature, so it's not available anymore. Though your car is L3 capable, you cannot turn it on, right?
Well, that's why you have to define the ODD, where does the feature work, right? So if you don't have definition of what the ODD it works at, including eventually at what speeds and whatnot, you're really not defining the feature capability or reach, if you will.
Right. I mean, really, it's compute benchmarks.
Is that so critical for benchmark? I mean,
the availability. Yeah, I don't know if it would be.
Okay. Yeah. For the benchmark, yeah.
So we're going to articulate a arch type that I think you would describe 3 different levels. So there's an arch type and it's got certain characteristics. And this is what it requires of these metrics. And this arch type may have limitations or not have limitations. To the extent that those can be articulated with it, great. But it's not a design guide. It's not, this is how you build an ADAS platform. It's just, if you built an ADAS platform that achieved level 2 or achieved this feature set, this is a benchmark of what you would need in these metrics to do.
Right, and maybe to be clear, it's a compute benchmark, right? So if you have this and you're trying to run this, tell me whether your compute unit can meet that and how much and what percentage of the resources, how much is left over to meet that. And if we do it over that range.
So if you define that as a scope, I would say then the sensors and the I/O is outside the scope of that, right? Because you want to see it's just what data is coming in.
Yeah, but I think so. You need
there's a dependency on the sensors and I/O, but
you still need to define how much data you get in.
What I'm trying to say, maybe on the trim levels, you define a separate reference sensor set. You say, okay, these are the sensor set I'm taking as a reference. Then you can say, okay, this is how much I need. Then if you change the compute, you can say, yeah, system A versus system B, you can compare with this reference sensor set. And on the different trim levels, you can have different sensor sets.
I think to make things benchmarkable, you actually have to fix the sensor set, because most likely you're going to be running this from a data set at some cadence, right? Yeah. So you won't be able to change the input on the fly between different OEMs and whatnot. So you have to have a very defined input, if you will, down to the, frame rate and resolution and the LiDAR and so forth. So that level of variability just precludes one-to-one, comparisons, and really any kind of benchmarking if you don't have a fixed input. And what are you expecting as a result, right? At this latency and this accuracy, I need to achieve these, actions, for example, if we are talking end-to-end, or these detections if we are talking kind of earlier, perception prediction.
Yeah, I tend to agree with what he's saying. What is
Predrag.
Yeah, Predrag, yeah, because that's how the gaming industry or the chip industry also works. They run that benchmark, they do the nominal case, and then they come back with the performance, and then the extreme, they throttle it up to the point where what point it will break.
I wonder if we can draw any parallels. You mentioned gaming, right? With gaming, because what does that deal with, right? You say you have a resolution, 1080p or 4K gaming, right? And you get certain fidelity of performance. Now, it may be overkill. You're getting 240 frames per second on 1080p, which is, I wonder if we can come up with something similar, right? In that metric. So we say that, okay, if you have this kind of data set, you have X amount of headroom, and then as you go up the data, just the input data size or resolution, if I want to draw a parallel, then you get 60 frames per second or 30 frames per second, which is the absolute minimum.
That's what I was also thinking, that how can you...
So exact same scenario from ADAS, if you look at the camera. The camera see a car stopped maybe 200 meters ahead or 100 meters, depending on the megapixel you have in backs, depending on how much you can compute, excluding the environment situation. I mean, I'm not talking about rain. That is where the sensors come into picture. How much details you have. That will depend on how fast you can brake. So that same scenario can be left as like braking in 50 meters or braking later. Like it depends on when you see it.
Maybe getting back to the sensors a little bit, though, I think one question is for system benchmark, do you need physical sensor interfaces connected or not? So the reason why that might be important, right? Cameras always pretty much go through an ISP, which is often now embedded in the SoC. Radar might well come over Ethernet interface, or LiDAR would, which has a slightly different path through the chip. That's a little bit different than our DNN benchmarks, where you just load up a bunch of video in memory, and now you're just checking how fast the MPU can process.
And again, even some ISPs may have certain blocks that are implemented in hardware, whereas some other ISPs do it in software as part of the driver, right? And how do you see warping and those sort of things?
Ethernet, right? You need to decode it, so it adds some more compute there and delays.
So do you make that as part of?
Yeah, and that's what I mean by defining the system, right?
Yes.
So we could define the system as everything runs out of memory, but we're going to run the DNN and the CPU and the GPU. That's one. It's a smaller system. It's a little bit easier to set that up because now I don't need a data source basically that plugs in.
But then
Ethernet's easy to emulate. Radar is like fake radar data.
But reading from memory still adds compute. So reading and then processing it, you are still going to have some overhead because of it.
Right, but you don't have any of the bandwidth of the initial data coming into memory.
Yeah.
So that's why I think I'm trying to grapple a little bit about how we then define system. The full system, I would hook up the sensors, right? Have it in the lab.
Yeah.
There's so many implementation details here that because you can stream, there are some ISPs that can stream directly into your codec. Some actually copy to memory. Some need to have their separate buffer spaces, and some can share. Some ISP drivers allow you to share with your main compute unit, or some you have to use a DMA to copy it.
Well, I think there's also a problem is how is a vendor going to get all those IPs in the same simulator, right? So if you require end-to-end, and let's say they don't make their own ISP, or they don't make their own either GPU or NPU, they produce a accelerator, but they don't produce everything, right?
Well,
How to glue all this together to get end-to-end solution, right? That can preclude, some people not contributing to the benchmark.
You have to balance on both sides of that. You don't want a validation environment that is so fragile that it can only exist in one place at one moment in time. It's got to be something robust enough that benchmarking can be done repeatedly with a comparable result. So there has to be a certain degree of robustness and portability to whatever you're articulating as your benchmarking environment. And that speaks to, here's a data set, use this data set, show me your performance. But on the other side, this data set has a whole stack of assumptions that may or may not be valid for the platform you're testing. So,
and that's up to the consumer of the benchmark to interpret, to say that, okay, if they want to optimize and, you know, have the data flow more directly, that's up to them, or they have, when they have the headroom and latency.
It does say though that
consume the data, and
as a association trying to build value in your benchmarking execution, you have to have some form of monitoring construct in place, because there can be and potentially will be gamesmanship done on your benchmarks. and we, you know, I've lived through those benchmark wars in prior lives as a refugee from the semiconductor industry, where you know, if you wanted to get better 3D game scores, you turned off the display output. And suddenly you had the fastest 3D engine in the world. It's just that nobody could see the results. But you published your score and everybody went out and bought your chip. So, you know, to understand that potential abuse environment, you've got to be able to articulate some of the parameters around which the benchmarking is considered valid. And, you know, here's the data set, here's the conditions under which we'll look at the test, and yes, you can publish these extenuating circumstances if you choose, kind of thing.
I like it. It's
I think we went through the same reasoning when we were doing the scenarios kind of recommendation. If you make it 2 unit tests, it's not valuable. If you make it totally end-to-end and everything is included, the likelihood of, you know, companies meeting those criteria is also going down, right? So you have to be somewhere in the middle where maybe you're not doing the entire system, or you're not or you're just defining it enough where things are implementable and not cheatable as well, as you mentioned.
Let me jump here to the compute element section of it. The idea again here is maybe I'm trying to, you know, ask the question, are there compute elements that we shouldn't try to include in the benchmark? Again, maybe to your point a little bit, the benchmark's too cumbersome and complex. You can't run it, then it doesn't kind of defeats the purpose. The MPU is the obvious one. We already have that with ML4. Probably GPU benchmark here in a system that includes infotainment. You're right.
Not just infotainment, AI is probably going to be used.
Can use GPU as well. There's some systems that's GPU for the AI and the display, or just AI. So,
is it a compute element or is it just the workload type? It's like FFTs that are around. You would just say, "Oh, FFT." I'm going to run a DSP, but not necessarily
compute targets.
Right. I see what you're saying. Like, the SoC vendor has the freedom to determine what their elements are.
You may want
right. So yeah, so maybe that's a better
another compute element. Yeah. It's not a DSP.
So what did you refer to that then as the
times again?
Yeah.
What your targets? Type. Your target is a targeting.
You don't care what it targets, right? You don't know what the workload is. The SoC vendor will choose where they run that workload.
Okay.
You don't have to define what they run it on. But
I guess you could have FFT in some cases. What's that?
For radar, right?
Radar. What's a typical CPU workload target then?
CPU can do everything. Everything, right? Not very well, but it can do everything. So for example, LLMs currently are preferred on, like, they tend to run more efficiently on CPUs because they haven't been optimized for.
But that's just the generation.
The generation thing, the transitionary phase.
Accelerators will catch up.
It just depends on how much memory you have, how hierarchical memory it is, right? That's going to determine your efficiency there.
Yeah, that's right. Yeah.
It depends also what the. I guess it depends how tightly coupled the software is to the hardware design, right? Because if you look at what happens in the mobile space, better optimize their LLMs all for CPU on the mobile phone because they know, because it's a third-party application, right? It's not a third-party app on the phone. So they optimize for the lowest common denominator thing they know will always be there. That's going to be CPU. They can't optimize for 10 different NPU types from every single mobile phone manufacturer. So I don't know if the same applies here or whether everything's kind of tightly.
So in other sense, for example, in the Android space, they do have abstraction layers. So Android HAL provides the abstraction layer for it. And most vendors will provide that. Yeah. Backend for those.
The thing is that I'm more inclined to think of compute elements in a sense that the operations that can be done on MPU versus GPU versus, let's say, vectorization on the CPU, that's going to migrate from one to another and come back depending on what operators you're using, right? So your hardware in place on the MPU is not changeable for a couple of years, right? Until you get the new one. So when you look at compute elements and you have certain libraries that you want to execute, it's going to be a combination of MPU, GPU, maybe even CPU, right? So that's, I think, a more fair kind of, at least in my mind, test or benchmark, as opposed to, you know, having a specific MPU or a specific GPU test, because you could have an MPU that's optimized for one set of operators, works very well for that, but then cannot do the other ones, and it needs to be offloaded to the GPU or CPU, and then they cannot really perform that test, right? Whereas if you allow it to actually do the migration, then, you know, you can have a compute element benchmark that says basically to accomplish this little task or subtask, this is how long it's going to take. And however you do it on your system, it's fine. But, you know, we want end-to-end latency and accuracy and energy that you use for that, because it also shows what your compiler is doing as well, right? So looking at it top down, I think you want to look at it more holistically. What does the hardware do? What does the compiler do? If you're just interested in the MPU itself, then you have to narrow it down to the operators that everybody can support, right? And that's usually going to be the more older operators and older models and stuff like that, that, you know, not everybody will be able to complete.
What are you trying to capture there, Steve? Look at, you know, the ASP there. Could you just categorize those as dedicated hardened accelerators, or case of us, soft accelerators? Accelerators, because that's a big part of our value.
Right. I mean, no. I mean, maybe from the OEM tier one building a compute system, I'm trying to just solve an ADAS problem, and maybe I have a radar that needs an FFT, but I don't care. I don't really care. So I'm not trying to benchmark the elements of this. Just trying to capture enough of the problem space.
What are the functions in that?
Yeah, right. Yeah. So, like, for example, GPU would be a display function. You know, I need, let's see how efficient the GPU is. Yeah. So I'm going to have 3 displays plus something else. So that's where we're kind of like, you know, if you have extra resources, then they need to somehow.
Yes,
The other one I wanted to ask about was the safety island. We think that ends up having an impact on the overall performance, or is that kind of like it's important? It's obviously important, but I don't know if it becomes a bottleneck.
It's big.
It's big.
Because the safety island, okay. My experience has been implementation of functional safety is a big pain. And overly cautious implementation of functional safety creates customer annoyance to the point where they are switching off the features. Now comes the question of a safety island, right?
With switching off functional safety features or?
No, they don't like it. There's too much of annoyance because anything due to whatever reason, we try to implement that in software, right? And overly cautious. Some companies become overly cautious. Oh, we have to be careful. We have to not do this. We have to always inform the customer of any this sensor is not working. That one all the time it's annoyance. And I have noticed this. But that being said, coming back to the safety island now, the safety island has a big performance
It depends on
implementation. Safety, and that's what I'm saying.
recognition.
Yeah.
So normally this kind of recognition and up to fast learning is lower than ACP. But fast learning conversion to the motion command. That's SCOD. The SCOD should be located on the safety island.
Right.
So the what until which level target of this benchmark is an issue.
That's the actuation part, right?
Yes, sure. And also at that time the actual receiving command side has also some safety functions. So for example, now is during accelerate at 1G, but the command is plus 1G. It's unbelievable or something like that. So in this case, the IC field of planning functionality. I don't think safety island affect too much.
At the system level, it does.
Sure.
Like I'm talking about the overall
system. So the overall system, if overall system includes brake actuator itself.
That's what I'm saying. Yeah.
Yeah. But
it even involves that. Because without that implementation in a vehicle, it's nowhere going to be going.
Yeah, but
looking at the feature, right?
But the braking control is the ACP independent processor. So it can be separate.
It's a good thing to know, like get the input from others as well, right?
Also, the automotive target doesn't include memory bandwidth. For using GPU, I've heard memory bandwidth is very important.
That's a very good idea. As I say, latency, right?
Yeah, but I think that isn't that covered under the IO and all of.
No, that's different.
Oh, okay.
I mean, I think if we've defined the right features or perception, then the memory bandwidth. But in terms of what we measure, I think the memory bandwidth is really interesting because you want to know. It's one thing for it to pass the benchmark, but you also want to know, is my memory almost at the limit or not? Good. Let me actually jump to some of these other slides as well. I think we talked about this one quite a bit, the scope, in terms of how we would define it, maybe a little bit away from the SAE level, but more towards some specific cases. Obviously, here I wanted to maybe just talk. Why don't we, it's already a 4:45. I know it's a long day. Many of you were flying in from, I don't know what time zone. So let's, here, I think what I would like to do is I wrote down kind of what would be this broad steps to achieve a system level benchmark. Why don't we go through it? And if I'm missing something, let's add it. Obviously defining the scope, not that we've done that, but we need to, the workloads, talk about that, the tools and the framework. You know, we probably use what we use in MLPerf. So there's this common mind that's here I showed as kind of the benchmark framework. Data and measure the KPIs often. We need to define the data sets. Here, what I mean by decoupled measurements versus full system is a little bit what I was referring to. Can I measure just like, you know, just the GPU or just the MPU versus just in the whole system run, you know, support it. Whether there's some software versus hardware. We didn't get into that a lot, but how we might want to use a system level benchmark to, you know, I don't know, have essentially a hypervisor benchmark, right? Like if everything is the same and all I change was the operating system or the hypervisor, is the performance change. And then the reporting and validation mechanism, I think we talked a little bit about that. But if we think through these steps, is there some either refinement or comment or additional step?
The portability of your workload.
Okay.
You need to make it platform agnostic or accelerator agnostic. If you are planning to deploy across multiple systems.
Yeah, that's important. Yeah. Customization will kill the effort. Also, another thing is steps to achieve this. For the work, this is not trivial work, by the way. To start up this workload, we will need access to, say, sometimes Hill or SIL and some tools here, there, some card maker or some simulators. So I think it's very important to get help from all people contributing.
How end-to-end do you want it to be as well, right? You want to go further inside or you want to go?
Yeah, so at least to start with, what is it? For example, suppose, is it possible I can have an open-ended Hill system where I can just put the CPU in and add the additional sensors with the connectors and run a software script that can simulate and give me some data out? Possible, why not? But the work has to be done, needs to be done to make it happen. Can we get some resources or some help, to make it happen?
We use our DBS software portability approach.
Yeah. Oh, yeah. That is.
Again, this is like standard ECU testing, right?
No. There's a lot of, see, every sensor has different connectors. You have to figure out, how to connect. Suppose there is a CPU, how do you connect that with some additional?
All that is done at the ECU level.
Working.
No, it's
sets
like,
sets a type of instruction.
yeah.
Take the output.
Yeah.
Seems it's okay in the link to has limitation because if you know the memory size or CPU core.
I know that's.
Still doesn't make sense.
That's why Hill said we do not know if there are any companies out there that are already. There is one company in Silicon Valley, it's for fully simulated. You don't need everything is in cloud. Kasar is the CEO. They have done very good work. If you want, I can open up discussion. Applied intuition.
Great. Well, let's. We actually have some time even tomorrow some additional discussion on system benchmarking. Maybe what would be good to get into then is a little bit also on the software side. We also want to talk a little bit about what a deployment benchmark would look like, sort of using like the SOAP approach. And also maybe a little bit more on, infotainment or domain fusion systems. So Austin will talk about domain fusion tomorrow. Might be a good follow on. And then also tomorrow we'll have an additional discussion on the foundation models. Frederick was done. He presented some of this in the spring. It was a really good talk on, and so we'll also do that. So I'm going to go ahead and we will end here. If anyone was online, I wasn't checking all the chat questions. Any final questions from anyone online?
Just a question on the schedule tomorrow. What time is the conversation going to be resumed?
Right. So this one will get this one specifically on this topic will get resumed at 1 p.m.
1 p.m.
Okay.
Awesome. Same link or is there a different link? Do you know?
I would. That is a great question. If you had signed up, I think you would have gotten an email with the link. Let's assume it's the same link.
Okay. Sounds good.
Maybe just double check the emails you might have gotten as well. So
awesome. Thank you. Thank you for our discussion. Great comments.
Yeah, thanks everyone. And yeah, it's a hard problem. That's why it's not, there's no solutions, but that's why we want to work.
That's why till now, for 20 years, nobody has come up with it.
Right. And, they say the best time to plant a tree is 20 years ago. But the second best time to plant a tree is today.
Yeah.
And that's, because we'll still be doing compute 20 years from now. And if the group, I don't know if I'll be meeting is talking about all the same stuff, we'll have failed in some way.
So I always joke, people say like how compute has changed. When I joined NVIDIA, stock was $3. Since then I left, and after that you look at all my colleagues who stayed back did not go anywhere. They are just looking at their account and being happy. So that's how the compute has gone, right? The years.
Yeah, no. Yeah. All right. Well, thanks everyone. Yeah, I think officially we will end in 10 minutes, but we'll end here. It's almost done. So grab some snacks for the road. And thanks everyone online. Bye.
Thank you.
Bye-bye.
I very opinionated observations.